So it's you finish at 325. Wait, hang on. 125. And that's the plan is to be done and go to the next presenter by then, but there's always a little bit of.
Well, I shot for 20 minutes on the slides.
Okay.
Time for questions.
All right.
So
I'd say
I'll be okay.
How many times have you come to a workshop?
This is my second. I went down to San Antonio last year, but we didn't present anything.
Yeah, I was down there too. So yeah, that was my first year also. It's good.
Yeah, I think the Emergent's been sending me for a while. And unfortunately, Brendan, who is supposed to be presenting this, is going through some like medical stuff. So trying to get together and present.
Okay. Good. So we're going to go ahead and get started. I hope everyone had a good lunch. So oh yeah, you said you didn't have your name on your slide, but yes, anyway. Go ahead when you're ready.
Okay.
Oh, by the way, keep the microphone near your mouth because that's one of the problems we've been having is, great, thank you.
Does that come across okay?
Yeah. The sound good, Jim? All right, yep.
Okay, cool. So my name is Austin Proby, and I'm from Emergent Space Technologies, and today I'm going to be talking about Summit, which is the scalable utility for... Okay. Which is the scalable utility for multi-mission integration and testing. It's an internal tool that we've been developing for our software development that really helps with sort of advanced flight software work. I forgot to put authors on the front slide, but this is done by myself, Brendan O'Connor, Graham Bryan, and Nick Merlin all from Emergent. So brief overview, I'm going to kind of touch on the motivation of why we built this tool, what the concept is, and then kind of go over the back end a little bit. And then I was going to try and do a demo, but that didn't work with the AV setup, so we have a video of a demo that we'll show. Okay. So Summit. The reason we had to build this tool was because sort of the small sat industry is moving in a direction of these companies that are producing commoditized buses. So you can, it's like Blue Canyon et al. You can go to them and say, I need a bus with roughly these properties, and they can give you a quote right away. And with minimal modifications, they can put your payload on it, they can stick your flight computer in it, and they have a defined API for interacting with the bus and getting information from it. So there's a lot less risk sort of in the bus development side of things for small sats. But at the same time, flight software is becoming more and more complicated. So there's new mission areas that people are trying to move flight software into that where the software has to do more things. So a couple of those are autonomy, network systems, and modular reusable software, which are all things that I think people here are very interested in. But when you kind of have more complicated software that has more interactions with more components that are coming from different people, there's more risk that ends up being contained in the flight software. And when you ask that software to do more things, there's obviously more risk there too. So the V&V tools that you use need to kind of evolve to keep up with this extra risk and find a way to validate the software that you're producing when it's more complicated than just running unit tests. So to meet that need, we've developed this internal tool called Summit, and there are a couple new technologies that make this possible. Wait, did I skip a slide? Nope, okay. So one of those is containerization. So that's tools like Docker and Kubernetes that allow you to run many parallel instances of flight software or build environments at the same time without having to have somebody configure each one. Virtualization, we had a good presentation on using QEMU to emulate flight software, not flight software, but actual flight processor boards in a containerized or in a software environment. But if you combine QEMU and containerization, then you can deploy multiple of these emulated flight software boards and test your flight software in its flight configuration in a virtualized environment. And when you combine that with containerization tools, then you can do that in parallel. There's also a lot of great Python tools that have recently become available to interact with, to manage automation, to interact with containers, and to use, essentially, to get information out of those containers and use it and store it with databases and interact with web front ends, which allows you to kind of make use of all the information that you're generating from all this large-scale parallel flight software testing. So anyway, and obviously Git, which we'd all be very sad without. So you can kind of combine all of these things to produce this tool that we call Summit. So the concept is that it kind of extends the concept of continuous integration to use in scenario testing. So a lot of people are familiar with the concept of having continuous integration where you have a server that when you're doing pull requests or something like that, you have a set of unit tests that your system has to pass before it will get integrated into the main software. But we've discovered that with extremely complicated flight software with lots of interactions, either your unit tests and everything that you run for your pull request will take 24 hours, or you can't test anywhere near the full set of things to actually be sure that that pull request is good. So we've kind of, and we don't want to have the developer sitting waiting 24 hours for a pull request to pass, because then it gets really hard to for them to work with the rest of the team. So we've kind of kept unit tests and that kind of thing in the standard continuous integration pipeline, but added this massively parallel tool on the end of it to do more testing after initial pull request. So we're leveraging scalability, we're leveraging containerization to provide that scalability and parallelization. So it's a tool that we really wanted to build it so that it can work with whatever flight software development we're doing, and we do all of our flight software development in Linux. So it's really just it can sit on top of any flight software development that you have in Linux, and because it uses containerization, if you have any kind of weird build dependencies or anything that's specific to your project, it can easily incorporate that. If you're familiar with deploying things in Docker, it's really easy to do, and it can scale really well and really fast. And then it has a bunch of tools to automatically manage versions and execute tests and save the results. So kind of talk about a little bit of the Summit architecture. There's a manager, so that's a project manager, which kind of, it runs the whole Summit show, orchestrates how the containers run, and gets everything started. And then there are containerized test managers, which are where each of the flight software environments run their tests. And then, so every project has a pair of components. So there's a project environment where the build and test generally take place, although there's a special exception for containerized testing, which I'll talk about in a moment. And then a project database. So it's not really useful to just be able to run a bunch of tests if you can't find out what happened in those tests. So it's really important that we save the results of the test. And we don't just save sort of pass-fail results. We actually get full state data for all of the tests that we're running and save that in a big database backend, so you can do forensic analysis on your tests after you've run them without having to go into the bowels of a server and find some logs. And then so on, all of that is sort of orchestrated by the manager, and the manager uses two tools to do that. It has the projects database, which is it's just a database that keeps track of all the projects that Summit is running, and then a front-end container, which is what we use to interact with Summit. So we found that, and we initially just had all these database tools and some Python plotting utilities, but people wanted to be able to see what was going on with their test really fast, and we found that the best way to do that was just to build hooks into the databases that were visible from a web GUI. So anyone can just pull up a web browser on any computer or tablet or phone and see what's going on with all of their testing. So I mentioned the one edge case for testing flight software where normally you have a test environment for your flight software that just exists within a container, and if your flight software tests run in that container, then it easily pulls into Summit. But we have a few projects where we need to launch thousands of containers of flight software that all work together and interact. And obviously you can't sort of have that kind of nested containerization without having massive performance penalties. So we have a specialized runner that can kind of break out of the test environment and launch a large number of other containers, and it sort of links them all together to the same database so that those containers can either all run separate tests or all run together as a large test, and then report the results back to the parent project environment. So I mentioned some of the web-based reporting. Summit deploys sort of this web-based front end that aggregates all the data from the project database and displays it for the developers. So you can see real-time updates from your sims and see how long they're taking, whether or not they're passing and failing. And so we have a few deployments of this that are running 24 hours a day, running tests, and you see all these real-time tests for whatever you're testing, and you can see pass-fail in real time and get reporting immediately, which is nice. And we also save tons and tons of historic data from all of the tests, which is, and we found this to actually be, from a developer's perspective, to be the most useful thing that the tool does, is it kind of lets you see everything that's going on with all of the scenarios that you're running of your flight software. So this vertical axis here is a set of scenarios, although this is a reduced set because there's actually more scenarios than we could fit here, where we're testing all of the flight software doing different things that it needs to do. And historically, you'll have kind of like unit tests where you will run a part of your flight software and make sure that your flight software, that component does the thing it's supposed to do. But as some of our missions have become more complicated and more intertwined, we've noticed that changing one component, if it has lots of interactions with other components, tends to have non-deterministic effects and can introduce flaws that you wouldn't necessarily expect, and there can be lots of unintended consequences. And this, because it's running all of the tests all the time, lets you know as soon as you've introduced something that has those unintended consequences on other parts of the flight software. So you can kind of see, here's an example of something where that happened. All these tests were passing. They've been passing for weeks, but then I think we're working here on sort of this complex feature, and one thing that we did here broke a whole bunch of other tests throughout the system. But because we had this utility running, we found out the next day that happened instead of finding out weeks later when we finally got around to doing a full day in the life test or something like that that's doing all the tests. So we were able to fix that we were able to fix it by the next day, most of it by the next day. One of the bugs took 2 days, but it just we knew when a change broke something, so it let us fix what it broke really fast, which is really, really nice from a developer perspective. So sort of how something kind of fits into our workflow currently. We do our flight software development and sort of standard development where we interact with the Git repository, and we have our standard pull requests. And this pull request is where we encompass sort of our standard continuous integration work. So that's unit testing for all of our merge requests to make sure that they pass the standard set of unit tests, and that they, it's not breaking everything, at least when you try and merge in software. But then that is automatically taken by the simulation control interface that automatically runs all these parallel simulations to verify that every component of the software is doing what it's supposed to do. It runs a bunch of multi-satellite simulations. It has high fidelity models, and it makes sure that it saves all this data into a database and makes sure that we're getting expected results. And if it doesn't, then it alerts developers. And it outputs all of that to both a web front end and other visualization utilities. So I don't know if once you start putting all this information in a database, you can do tons of fun things with it, because there's all these great APIs for grabbing data from databases, thanks to all of our friends in the tech industry. So we have visualizations. They can just grab data from any test that you've run historically, just grab it out of the database and visualize it on any computer you want to, because all the sims are stored with a unique ID, and you don't have to plug anything in. It's really great. And anyway, that feedback goes into developers, which influences their flight software development process. So it's just kind of adding all these new capabilities onto our development pipeline. So, it sounds like there's a lot of complicated things, and there's a lot of complicated things going on in the back end, but we wanted it to be as simple for developers as possible. So you kind of just all you have to do to deploy Summit is build sort of this meta repository with your flight software here, and then all of the scenarios that you want your software to test. And from our perspective, a scenario is just a sort of a bash command that executes whatever tests you need to run for your flight software. But it doesn't need to be something simple. It can either, it can take days, or it can spin up a ton of Docker containers that do all sorts of complicated things. but as long as it outputs, an expected JSON format for the final results, Summit knows how to deal with your scenarios. And these are some fancy things for fancy sim that I'm not really going to talk about because I don't have time. But they're not really relevant for Summit. So you can run, even if you just have a really simple flight software program, you can just populate these top parts and it'll be running in Summit almost instantaneously as soon as you push it up to the server and add it to the project's database. And I mentioned, feedback for developers, and so this is what some of that looks like. They're configurable analysis pages. So I mentioned, a lot of times after a test fails, a developer will have to go into the logs to figure out what was going on in the test. But what we've discovered is that if there are certain things that you find developers are looking at a lot, so for one of these, multi-spacecraft configurations when in an oil or hill frame or delta Vs, we found out people really cared about those for a lot of the tests, so we added them to the web front end, and because we have access to all the historical data from all of our sims, it's really easy to grab and just populate and put it on the web front end, so that instead of having to go through some process of grabbing the data from a server and running some scripts to plot it in MATLAB or Python, it just, you load a web page and it's there. And then we also have hooks for all of our sort of developer tools. So we have a internal chat server, and we just it's really easy because it's all web-based to send data to that chat server, so you can say, hey, this test failed, this test passed, and alert relevant people based on the results. Okay, so this is where I would be doing a demo, but I think we have a video instead. Okay, so this is the Summit landing page, if you play it. Okay, so this is what it looks like when you go into, this is a pretty simple flight software project that we're just beginning. So it just has a few tests that take a while to run, but they're not a lot more complicated than unit tests. And you can see the results, and it saves them, and you can scroll through them, and it's easy to see. But so I think we're going to go look at a different flight software project that has a little more going on. Oh no, I'm going to look at the historical results data. So you can see that table. This one has significantly fewer scenarios than the one I showed in the slides, but you can still see that historical data. So here's another project that has more going on. So this is for DARPA Blackjack. So we have this is one of the instances where we had to run tons and tons of flight software containers. So there's actually several hundred flight software containers running in some of these tests that are all interacting with one another as a part of I think this one is a 90-sat constellation. So here it is. Here's the web loading all of the spacecraft position data, and then you can show the space vehicle final positions if you want and look at them. And then I think I'm going to go down and look at the ground track. So these are little custom web apps that we wrote and inserted for this project because it was, it's a project-specific thing. But now we have these little web apps that we can add to any project. If you want to get ground track, you can get ground track, or if you want to get a constellation view, you can get that too. As opposed to like other projects where we had like the delta V and that the RIC frame information. And so here we got the historical test data, and we also have like filters. So if you want to, you can see what happened in a test, but if you want to just look at tests that fail, we got filters to sort of query the database in specific ways to get all that information right away. And if you click on those, you can actually go into log information, but that would be impossible to read, so I didn't go into there. But yeah, so we found it's a very useful tool, and it's not really some of our recent autonomous multi-spacecraft projects that we've been working on, we could not have accomplished. We couldn't have finished the software development without this massively parallel testing because our test team was just like getting really, really overwhelmed with the amount of tests they ended up having to run. So we figured out we had to do this massively parallel thing, and then we built this tool around it, and we think it's pretty cool. It's been helping us out a lot. So, anybody have any questions?
Questions? Oh, Jason, I think you get a prize for asking the most questions.
I was going to wait for somebody else. Were you all going to make this open source project?
We are not sure if we can because of who paid us to develop parts of it. Yeah.
Just a quick follow-up to that. So You published a white paper or anything with some more
No,
details?
This is sort of like it's like a pre-alpha version of something that we just developed internally. And we're not trying to like sell it to anybody or anything right now. We just like, we thought we think moving to this sort of massively parallel containerized testing is going to make a lot of sense. And I think it's for sort of like the flight software industry. So we just kind of wanted to let people know what we were doing.
Yeah, thanks.
Other questions? Okay, great, thank you. All right, so we just set up another tour this afternoon. We get finished with the workshop today, which will be like 4:50 p.m., right? So we have the mugs and modeling that's going to happen starting at that time up in the art room. And if you want to go on a tour of Straight to Ale, well, let me see a show of hands. Who wants to go on a tour of Straight to Ale? Which is right here, basically like within 100 yards of here. So like one tour. So the people who want to go on a tour, you can, if you want to go, we're going to meet right out here by the front doors, like right after the workshop today, and we'll leave in about 5 minutes from the time we finish. Okay, so just meet us right out here by the front doors, and we'll walk over there. It'll take about 20 minutes to go on the tour. So if you have 20 minutes or 30 minutes, we'll be done. Great. Our next presenter is Deanna Whitehead.
Okay, hopefully I've got this mic in a good position. It's kind of sneaking its way down, so I apologize about that. So I'm Deanna Whitehead. I'm from Marshall Space Flight Center. Until about 2 weeks ago, I was the SLS Flight Software Design Team Lead. I've just moved over to support Gateway, so I'm excited about that too. And I just want to say I hope everyone is having as much fun in here as they are out there. They're having a lot of fun. So anyway, I'm going to talk to you today about some of the steps that we've taken to ensure that our flight software is highly reliable. Okay, so just an outline. I'll talk very briefly about the SLS vehicle because I'm sure you're all fairly familiar with that at this point. Just our flight software overview, our modified Scrum process that we use, how we very tightly control our changes, and then some of the steps that we take for every software change that we have. And then I have some inspirational propaganda at the end if we have time. Hopefully it'll work. Where do I click it? Where do I point it? Okay. Okay, so like I said, you've already heard about SLS, our powerful rocket that's targeted for deep space exploration. So the point I want to make here really is that this is a national capability. You know, we have industry partners and centers all across the country that's contributing to this. So we're proud of it as a nation. We're contributing to our nation's economy. It's very important to us at Marshall Space Flight Center and in our software design branch to make sure that our mission is successful. One thing I will mention, like I said, we're spread out everywhere, and we've been given the opportunity to develop this software in-house, which is a big deal because most of the other pieces and parts are being developed by a prime contractor, but all of this work for the flight software is being developed here at Marshall Space Flight Center. Okay, so we've already talked a little bit about our NASA procedural requirement, 7150.2. We're on Rev B for flight software. You know, that helps us determine what classification our software is. So in this case, it's human-rated flight software, so pretty easy determination, and that's going to be Class A, safety critical. You know, our software is controlling some safety critical functions. We could damage the vehicle, you know, we could cause a loss of mission, so we have to do a lot of rigorous activities to ensure that that doesn't happen. We're using the A-Rank 653 standard. We're developing in VxWorks 653 that offers a partitioned operating system, which gives you protection in space and time. So your memory is protected, your time is protected. We're also developing in C++, which, you know, when we made the decision at least was a bit of a change to move from C to C++. We're still under C++ 2003. I think someone mentioned earlier, you know, some of these standards are centered around those older versions, and ours certainly is. Our coding standard is based on the JSF++ standard. And we have about 50,000 lines of code, so it's not huge. We have some auto-generated data tables and headers and things like that that we're not counting in that count, but as far as our handwritten code, it's about 50,000. I also meant to mention, obviously, we're CMMI level 3. That's required for any Class A safety critical software. So I'm actually going to skip ahead one. I'll come back to this. So even though we haven't launched yet, for the flight software, we're in a maintenance mode. That means we've released what we think is our flight candidate of our code. So we've hit that milestone. And so because of that, all of our changes are very tightly controlled. So we have what we call the avionics and software control board. Now, of course, there are boards up above that, and I'm not going to get into all of that, but our closest one is this ASCB. And what will happen is that a problem request or a problem report can be submitted through this board. They could come from other disciplines, so maybe GNC or maybe the engines or, you know, any number of places can come in through there. So we have a board of people who'll decide if that is a real problem, if it needs to be addressed right now, what ramifications or, you know, if there are mitigations that we could do to control that. And if they agree that we need to make a change as a result of it, then it flows down to our team. So the SLS Flight Software team will get a change request. And so then that's analyzed by our requirements team, our design team, test team, everybody to determine what kind of changes we need to make. Okay, so if that's all approved, then it flows down into one or many design team CRs. So that outlines exactly what we're going to change in the code. Okay, so we have a change management tool called Serena or Solutions Business Manager, and that helps us track any PR, CR that we have that enters our system. Once all of the approvals are given at those various levels and the design level CRs are moved to an implementation state, which is determined by the lead, the developers are ready to begin work. So we're using Subversion right now for our code repository. And so each time that we get an approved CR, I, as the design team lead, would create a branch for the developers to go off and do their work. Pretty common paradigm there. We have, unfortunately, we don't have a completely integrated system for our change management and our code management, but we have some specialized code that we've written that allows us to track each commit. So anytime a developer checks in, a note is added. Oh, louder. Okay, thank you. A note's added to the CR. Is that better? I'm just going to hold it. Okay. To the CR so that we can go back and check, okay, exactly what changed. Okay, and so that's been very, very helpful as we're trying to stay on top of exactly what's changed. Okay, so now I'm going to go back to my previous chart here. So we use a modified Scrum lifecycle, and part of, you know, the reason I wanted to go through that whole, you know, board approval and everything before I talked about this is so that you can see why certain things are happening outside of our normal sprint cycles. So all of that, you know, PR coming in and deciding if this is a worthy change or not is happening outside of our sprint cycles. So once that is decided, then we work with our sister organizations for mission and fault management, vehicle management, to determine if there are algorithm changes, requirement changes, or whatever. Once all of that's decided, then we follow a pretty basic sprint cycle. The only thing that's a little different, we do mostly a 6-week sprint cycle because we're including a week to integrate. So we've found over the years that it takes about a week for us to integrate all those CRs, make sure that our system response is still what it's supposed to be. And then we have our configuration management team that creates our releases. So they get a week too. And what happens once we have that release is it goes to our formal testing facilities, which I think you've already talked about, the SIL. Some people got to tour yesterday. Okay. So, like I mentioned before, we have a coding standard that's based on the Joint Strike Fighter. We have an automated tool that checks that. We're running it every night on our integration branch. We're using a tool called PRQA to do that. We also leverage our IV&V folks. They have some other tools, so every time we have a dev tag come out, we get it to them and they run it through their tools as well. So for code coverage, we have the pretty common branch and statement coverage, but we've also committed to 100% MCDC coverage. So that's the multi-condition decision coverage. So it's a little above and beyond, we think. Again, that's executed every night. For each of these, we get an email every morning telling us if there's a new failure, how many tests were executed, and all that. Also, we have functional testing. So we've written our own test harness in-house to allow us to do module level testing. So that's kind of just function level testing. And we have over 1 million of those tests that run every night. So gives us a warm fuzzy when we see those all pass. I didn't put on here, but I'll also mention we have a trace report that runs every night. So we make sure that every requirement is traced to our design and to the code and to the test and back. So we check that every night too. Okay, so once a developer has gone through all of those steps, the CR will go into a quality check, and that provides a peer review for each change. It makes sure that the code was changed as we expected and no additional changes were made, so we can't sneak anything in there. It checks that the unit testing results are 100% like we expect, the functional test results as well as the static analysis. So we do all of that before anything is promoted to our integration branch. Also, we get ready for doing the integration. So the developer will recommend what kind of testing they think should be done for each CR. So some options are fly out. So we have another tool that allows us to queue up a scenario and fly the rocket using Artemis and Maestro, which I believe you heard about this morning, and then analyze the results pretty quickly. We also do a lot of batch testing because we have an asynchronous system. So we really need to run things multiple times just to make sure that we understand what the behavior is going to be. Okay, so once all of that's been done, we integrate the CR. We make sure that all of those overnight tests will run on the integration branch with everything else, because sometimes we see new errors when everything is integrated together. We run any simulation or extended unit tests that need to be run and notify the developer of any issues that we see. We just continue that until we're all happy. Okay, so just a summary, lots and lots of automated testing. We're continuing to add more every day. We're continuing to do off-nominal scenario testing. We have some developers that are really good at coming up with bad day scenarios that we're testing. Let's see. So one thing that we've talked about previously, but with the system integration testing, we're seeing new questions and issues come up as a result of that. So we're glad to have additional people taking a look at everything from a different perspective. Okay. Is there sound? No. Oh, there's no sound. Okay. Well, maybe we'll just skip this. This is a nice video. I think it's called We Go, so it's out on YouTube. You can go out and see it for yourself when you have a chance. So if you have any questions after this, you can feel free to contact me. There's my contact. There's a little article about what we do here at Marshall. So that's it.
We have time for questions.
Thank you very much for the presentation. I've actually a couple of questions, hope you don't mind me asking. So given your experiences on SLS, and you said you were going to Gateway, what lessons have you learned that you're taking to Gateway to do its development effort?
So there are a couple of things. I mentioned that our coding standard is modified JSF, so it's custom. Which means that we've had a multitude of problems getting our static analyzer 100%. So I think one lesson learned is to go with the standard if at all possible. Another thing is that, we didn't do all the automation from the beginning, because that takes time. You want to develop the code instead of getting maybe that whole testing framework completed. So I think that's a lesson learned as well, is just to do as much of that up front as possible.
So it's actually my second question was, do you do test-driven development since you have an agile workflow for, okay, and then the other is, I'll speak for Jake, can you guys consult on unit testing for Core Flight?
Oh, can we consult? Yeah, I think that is something that we're gonna work on. Yeah, because we're using Core Flight system, so we'll be doing lots of unit testing and everything too. Yeah.
Other questions? We'll go back here.
Yeah, I'm just curious about the the heritage of the flight software for SLS. How much of it was really new versus legacy from a previous project? And also, do you know or project what that percentage will be for Gateway? Will that be 100% new?
So there was some heritage from Ares, which was Constellation that was canceled. But other than that, it was completely new. We used some, we do have a couple of people who worked Shuttle, obviously, and even Apollo. And so we do leverage their knowledge to help us with things that they learned over the years. But it's a completely new architecture, so completely new code.
Yeah. I'm not sure I can completely understand why would you need to go to a 6-week sprint when you have like 1 million set of unit tests plus integration tests. Why do you need to have 6 weeks? What is the problem in the integration then? Hardware?
Sometimes, because we have 2 lines in our lab, so there is some hardware timing limitations for us to run all of our integration tests and everything. A lot of it is just coordination. I'll be honest, just coordinating, outside of our organization, just to make sure that we're doing exactly what our, I would call them our customers want us to do. Because like I say, at this point, we're making changes because there was an issue found. Lots of times it's a hardware workaround and things like that, and that slows us down. But you're right, and it does help. But I tell you, every time we do a sprint, we usually face some different issue. So when we get everything in our integration branch, there's always something. And so we often deliver early, but we allow ourselves that time.
Okay. And do you also have integrated hardware for the nightly builds? I mean, you go continuous integration down to the hardware level?
So we have engineering units that we're running on.
Okay.
Is that what you mean? So,
Yeah,
so
I
we
mean-
are running on that hardware, but we're not running like in the SIL every night, obviously. So not with that hardware. We're running with Artemis and Maestro, which is our simulation environment. But we are running with that environment.
Okay, thank you.
So there are a lot of really good and useful process steps here. I'm wondering if you could say which one did you find the most useful, and which one did you find the least useful that you might reconsider in the future?
Interesting. Let's see. I got to look back at what all I told you. I really think just having all those nightly runs, that's probably the most useful, just to ensure that we haven't introduced any bugs. Also, like I say, and I know it does extend our sprint duration, but allowing that time for integration, I think that was a hard lesson learned. But let's see, the least, waiting for all those inputs to come in, that's the least fun, right? We have to do it, though. Is that it? Oh, okay.
So when you were talking about static analysis tools, do you only use one, like the PRQA Helix, or do you use multiple?
We only use one ourselves, but like I said, we have our IVMV facility in Virginia, and they have multiple. Like I know they have Clockwork, and I don't remember. I think they have a few, and so they always run those for us for every dev tag that we create. So any possible release version, we're getting all that feedback. So now it's not specific to our coding standard, but if they find something that's an issue, we want to fix it anyway, even if it's not violating our standard. So we always go through that. And over the years, it's gotten less and less the things that they find, thankfully.
Is IVNV open to all NASA centers to have them analyze code?
I think they are, but obviously they're restricted on time. So I think that goes back to your software classification. I don't think they're going to step in on anything that's below a B, maybe a C classification. So I think it's restricted in that way.
Thank you.
Mm-hmm.
Yeah, just to answer kind of that question, and I don't know, there's a couple other IVNV folks here, but it is based, it's independent, so it's not tied to the projects, and it's based on, of course, limited funding and whatever, so they set goals for what projects are going to do, so that's kind of how it works, and end up with like I said, during my presentation, the Class A software, especially mission critical or manned space flight. That's why SLS, Orion, Kennedy are on that list. And then usually other very high profile, high dollar missions like James Webb.
That's true. Now, we've had something recently that was classified as a B, and it wasn't as high profile. So, we do try to make sure that more than anything, it's based on the function. If there's anything if you're controlling a heater, it doesn't really matter what you're doing. But there is also a monetary boundary. If you go above this, it's going to be a higher classification. If you fall below, your lower classification. So, it also it goes into the altitude. So what kind of airspace you're actually going to be in, and things like that too.
Questions? No. Thank you, Deanna. Our next speaker is Sean Phillips. So, Sean, you were here just a minute ago, so that microphone is, you may want to hold it. That mic stand doesn't work very well either, so.
Hello? Is that going to work? Let me play with this a second. Okay, so my name's Sean Phillips, and I'm also working with the Space Launch System flight software at Marshall Space Flight Center. I'm the project lead at this time, and as Deanna mentioned, it's an in-house development, and we're very proud of that we had that opportunity to develop that software in-house at Marshall. And of course, as the lead, I'm responsible for all the phases of software development, though I'm focusing on testing in this discussion. But development, of course, covers the whole life cycle, from requirements through design and verification. And so like Deanna's here, she's now a former member of my team. And there's several other people in the room that have supported SLS over the last several years. My topic here is the discussion of switching from manual versus automated analysis and verification. And it's a little different than what Deanna's talking, because I'm talking the integrated build after delivery informal test. This transition is actually in progress. We did not start with tools. That's been a big lesson learned, even at this level of testing. It's a time-intensive, highly inefficient process we've been following. We have been able to get through our first formal qualification testing, though, but it's taken a lot of incremental activity, a lot of time, and it's actually our largest team is our test and verification team on the project. As Deanna mentioned, we're in maintenance now, and as we start looking at Artemis 2 and beyond, we realize that we have to get automated to posture ourselves to be able to more quickly deliver changes, even for Artemis 1. If we don't get there, the testing is what's going to slow us down. So, as an overview, I'm going to talk a little bit more about flight software context and the vehicle. Deanna covered a lot of that, but I have a couple of different slides. I'm going to talk about our current development and verification strategy, a little bit about how our manual verification process works, and then what we're going to do to automate our process. And I have a few words on some forward planning. So where is the avionics that the flight software actually runs on? It's actually in the core stage avionics. The flight computers are up here in the upper ring. This is the vehicle blown out. So of course you guys know about Orion. There's the adapters, launch vehicle stage adapter. But there's also avionics in the booster and on the engines and up and down the core with things like the MPS and the thrust vector controls and RGA, RENUs. All those pieces of avionics exist all through the vehicle. So just an overview of the different kinds of software we have. As I mentioned, the flight software resides on the flight computers, and we actually have 3 flight computers. They're in a voting architecture. And we refer to that, often you'll hear one of us talking about our FCOG, that's our Flight Computer Operational Group. But other software includes the ICPS, and the vendor ULA is providing that software. The RENU, which is our nav unit, comes loaded with software that's critical to our nav positioning, and we use data from that in our GNC calculations. Also the RGA, the rate gyro assembly, comes from Honeywell, and it provides our rate data to the flight computers. And then the engine controllers are heritage. They've updated the software quite a bit, but there are 25 engines with updated software. Whoops. So, just to let you know, we actually are developing 2 CSCIs. We're developing what we call, and we weren't very original with naming, the Flight Computer Application Software, CSCI, which provides all our pre-flight, pre-operational activities and all the flight critical and non-critical software functions necessary for on-pad, pre-launch operations, processing, integration, all that activity. The launch countdown where we go autonomous, as Tia mentioned on Monday, and then engine ignition, and then ascent of the vehicle through a couple modes of flight. The grid run application software is very similar. It's actually built on the same code base, but instead of running the GNC software, it executes a predefined thrust vector control, actuator position profile, and a predefined engine controller throttle position profile. So it can be executed in a hot fire on the B2 test stand at Stennis. And that will be a test of the core stage that you will see hopefully later next spring before it's shipped from Stennis to the Cape for integration into the SLS vehicle. So as Deanna mentioned, we have several development standards. We have to follow 7150.2, and as she mentioned, we're on B. And I noticed out there that the NASA table has several copies of C, but I still have my B copy because that's what we're following for Artemis 1. We haven't committed to a time frame yet for upgrading to C. Thinking to be with Artemis 2, but we haven't committed yet. That levies requirements on us because we're Class A safety critical, and we have to show that compliance. And we do a lot of that through our software development plan, has a tailoring matrix, and we point to all the different artifacts that support our compliance. And then also, critical as being Class A is we have to meet the CMMI maturity model for development version 1.3, and we were assessed at level 3 for all process areas earlier this year, at least the 3rd time, maybe more. I can't remember how many times we've done it now. I believe we're stepping up to version 2.0 for the next round. I think that's required. Okay, similar to Deanna, I also wanted to just touch on our agile development. As she mentioned, we do requirements development outside of the actual development sprints, but we also do, and my focus is more on the test side. So there's a lot of testing done within the development group itself as it builds up the changes. But the actual verification and sign-off is done against the SRS, is done by the test team. And so they are independent. They're not the developers. They're allowed to talk to the developers, but they are independent from the development team and have to have a lot of knowledge about how the system operates to understand how to set up tests. So this is a chart we share at every one of our test readiness reviews to show the buildup of testing. As Deanna covered quite thoroughly, there's unit testing, both code coverage and functional unit testing and MCDC coverage testing done down in the design team, and this integration testing. All this is we have clocked over 15,000 hours of testing in these venues at this point, and we continue to run nightly, as Deanna mentioned, and that's a critical foundation for all of our verification activities. At this transition point is when CM builds the dev tag, and there is some, it's not any verification, but they do a confirmation flyout and verify at least that it works the way we thought it would, that the build is the same build that the development team gets. And that's been important because we do want it independently built by the CM team, and we need to make sure it's the same build. Then we enter into the design, T&V team's venue, and I'm going to talk a little bit about what a DLR is versus this testing. But this comprises our T&V activity, And this is the requirements verification in our test lines. Just like the design lines, we run in a simulation environment with Maestro and Artemis, and we have the FCOG EDUs. We have 3 EDUs in both of these lines, and everything else is simulated in the verification labs for flight software. And as you notice, the fidelity of the venues increases. So down here, we're doing, sometimes this functional unit testing is done on the individual developers' workstations, and it gets built up even in here to the triplex level. But as we go to this venue, it's just the triplex. And as you know, the cost and schedule starts going up. So these tests, you can run all of our unit testing overnight, and it takes about 12 hours now to run all of it. This testing, which I'll talk about now, a nominal run where you do an entire flyout takes at least 15 minutes. And there's some extended tests just to verify other capabilities we have to do that take hours to execute. After that, we deliver to the SIL. You saw that if you saw the tour, and they do integration testing there. It's comprehensive, what's called DVO verification. That's where all the stakeholders have levied their requirements against the system, and all of them, including us, participate in a review of the data that's generated in that lab and provide feedback and review. We've just completed phase 1 of that. And there has been feedback that has led to some changes, and we actually have a maintenance release going through this cycle right now because of results in phase 1 verification testing. Some hardware driven, as Deanna mentioned, where hardware doesn't work quite like we thought it did. And in some cases, we missed a couple things. After the SIL, there's also a sister lab called the CITIF that if you saw the tour or the picture Tia put up the other day, that's a stage representation, similar hardware, where we'll be doing a green run, similar environment. We'll be doing validation testing with the GRASS CSCI here very, very shortly with the stage controller, which is the ground control for the green run test. After that, it gets integrated on the vehicle. It's going to be used for green run, like I mentioned, and then it will be used initially for ITCO, which is some early testing when they start integrating the vehicle. It's also then, of course, be used for EM1. So the first flight is our ultimate validation activity. Wanted to also give kudos here to IVNV. Their S3 environment that was mentioned in their earlier talk has been very useful in finding some unique problems that we couldn't have identified with our testing environments here. They're able to, because they simulate the hardware, they can actually emulate process type failures that we cannot do on the real hardware. It's been very interesting results. So, as I promised, little definition of how we set up our requirements. We have 2 levels of requirements. We have black box. Those are the ones that exist at the FCOG level. You get it's the response to an external stimulus at the system level. So if you get a power on command to one of those avionics boxes, what is the flight computer going to do? It can be much more involved, but that's a simple version of a black box requirement. At a design level requirement, and we call those DLRs, the behavior and stimulus is only internal to the system. So those are module level. What does the propulsion system do specifically when it sees that power on command, maybe to a propulsion system box, and it may not be, and it's not visible outside of the CSCI. So our test team tests both types of requirements, and verification of both of these, of the entire set of about 1,000 requirements, is required to complete our verification activity, and we own 1 DVO that's for the verification of all these requirements. I'm not going to talk DLRs in this talk anymore much, because the DLRs, we follow a similar test philosophy as the unit testing. That's required. You can't look under the box if you're running the system as a whole. You're looking at data that's coming either out of the simulation environment or down on telemetry. So here's just a little representation of the differences. So here, the black box is communicating with the simulation environment on the real buses, so they're all running a copy of flight software. They're all sharing data, and Artemis controls the inputs to all those boxes. The DLR testing, it's on a single board computer, and the harness executes the module. And we provide test vectors, and like the design team, these test vectors were written by the test team, and they execute the module at that low level. So both of these have documentation. Because we are this Class A, we have to produce a test plan. In the test plan, we trace our requirements to test procedures. Test procedures are actually captured in doors and in Subversion, where they're actually controlled. And then we have to produce a test report with all the results, pass-fail for every single requirement. So going on to why we want to change what we've been doing. This is our process flow for verification. So we develop the test plan. We start developing test procedures. This is a manual process right here, and you guys probably can't read it, but it's the logical steps when you're generating a test procedure to operate the lab and create the data for each test case, and I'll talk a little bit more about how we break those down. You go and you develop what it takes, and so I didn't really mention it, but of course, to do those stimulus, a lot of our requirements are off nominal, so you have to inject a fault. So you have to write fault injection scripts, and you have to build all that. Then you dry run, and then you do a manual data analysis, and you repeat this iteratively until the results are either pass as you expect it because you finally got the test right, or the test is right, but it fails. And you iterate on that process. This is always manual in our current process. And just as an example, currently a full flyout is about 12 gigabytes of data. So it takes some work. So we do all that build up, we get all the procedures written. Every single one of them is reviewed by multiple stakeholders outside of the flight software environment, which is another reason it's not in a sprint. We've tightened up on their allowed time, but it still takes longer than it should. So eventually we build up that whole suite. We have a TRR, and we go into formal test execution. So we do batch up, even in this mode, we do batch our runs. So often overnight we'll run 20 to 40 test cases. Even at 15 minutes apiece, that's about the limit of what you can really do. But you don't know if they passed or failed till you go, again, do that manual process. If you're lucky, some of the smaller nominal cases take 3-4 hours. But a lot of them take multiple days, especially the more complex ones requiring multiple permutations. So we've been working with this paradigm for years. We've known it's not ideal. We've known we couldn't support it. And while there is some analysis tools, and there's a few we've used here, we didn't have anything that we called accredited or formally verified that we were willing to stand on to say, yes, this is good enough to support a Class A verification activity. So, whoops, sorry, went too fast. So this basically repeats what I just said, just in some words, just emphasizing that it's manual. You got to pull the data. You got to manipulate the data. You actually pull it into an Excel spreadsheet, and you have to manipulate the data. And then you have to evaluate it against the pass-fail criteria you documented in your test procedure. So just a high-level, very, very high-level overview of how this process evolves. Sorry, giving away the punchline. I'm not good at this. So this is similar to that example earlier, very, very simple. At some kind of time, the FCAS shall send a command to some kind of box. So that's a very, very simplistic one. A lot of ours are, like I said, off-nominal. There will be multiple off-nominal scenarios that could trigger a certain kind of abort or caution, and there'll be fairly complex requirements that require multiple test cases to verify. This one's pretty simple. You'd look at the bus data, you check the time for that time you're looking for. You check it that at that time that command was in the data packet to the box, and you'd create that test package for the community review. You know, this would be the pass-fail step. that the command was found in that data packet right where you thought it would be. So that one, pretty simple, but, repeat it 500 times. And like I said, this is a simple one. There's many requirements that require multiple permutations to fully test. So there is multiple test cases. I don't know what the average is, but it is over 1. We have several that have 64 or more test cases because of the complex nature of the software. So you'd see it in the plan, the trace, identify the methodology, and by the way, test is our preferred methodology as Class A software. You can inspect, and we do have a handful of inspections, and I don't think we have any demonstrates. Our goal, like I said, primarily is test. And then in the test report, you'd see the pass-fail results. So here's our proposed automated process. You're still going to have to develop all those test cases because you got to develop the pass-fail criteria. You need to know what you're trying to do, and you have to develop how you're going to do it. But instead of doing that manual analysis every time, we're going to develop a module that's going to work in a tool to confirm that pass-fail status. And it's going to pull, and you're going to generate all the associated artifacts. You're going to have to develop the fault injection scenarios and all those still. But then when you do the dry runs, this automated tool will extract the data and evaluate the data against the module logic, and then it'll be able to tell you, hey, it passed or it failed right then. At the conclusion of those set of batch runs overnight, the test engineer is going to be able to come in and say, hey, they all passed. Hopefully, if you're after TRR, they all passed because that's our goal, and be able to put that right into our STR. And so that's our goal, and we actually are well on our way to meeting that goal. We have an automated tool that has been in work for several months. It is an in-house developed by the tools team. We have a tools team. Class C safety critical tool is going to be certified, and we actually had the TRR yesterday. So they're in the process of testing it right now. It has 2 modes. I keep hitting that. Uh-oh. I'll keep talking, but I need the charts back. Can I do that myself? Okay. Has 2 modes. It has a command line interface mode and a interactive mode. The command line interface mode is what I'm going to focus on here for a second, but the interactive mode is going to let you do on-the-fly data analysis. The command line mode is going to let you build these modules, and they're going to be available. You can write them. They have to be written, their code, in either Python. Right now, we're going to upgrade it to support C++ also in the next iteration. And these modules will be executed from the run data. So the service will pull in the run data as soon as the run's complete. It develops a database based on the measurement list that you pick. So there's measurement data. You have to tell it what data to pull out of this data set. And then it will run the module and report that pass-fail output for every one of these. So that's our goal. And like I said, we've been building that up. The tools team had their TRR yesterday afternoon and got approval to go forward into testing. Hopefully that will be complete verification by early January, because we actually have a use for it coming up soon. So this is my last slide, well, second to last slide, but so a summary and a forward plan. So we really felt that automated testing was where we needed to go to reduce human interaction. Every time you do that manual analysis, you have a potential for human error in reviewing the results. And by being repeatable and automated, it's going to allow for easier regression testing. It's definitely going to improve our test data evaluation time frames. It right now takes weeks to get the analysis complete and build that test report. And it's going to improve our overall schedule efficiency and turnaround time, because once this is deployed, we're going to start building modules to support all the testing. So hopefully, sooner rather than later, we'll be able to pull a whole regression test and just execute it with these Sherlock modules. So our forward planning is to complete the certification of the command line interface. That's actually what we're testing first. Like I said, our goal is early January. We have a pilot lined up. We have configuration data that supports all the different launch windows that are going to be available, and we have to confirm all that data. And that was one of the reasons we realized we have to have this sooner, like now, to be able to do those data confirmations without taking months. That piloting effort is supposed to happen at the end of January. That's why we gave them the goal of being done by mid-January. And then, as I mentioned, that forward plan to start building a suite of modules to support regression testing. There's even some long-term planning not mentioned here. Maybe try to integrate machine learning to even help with some of this data analysis going forward in the future. That's a little bit further out, but it's on the radar, and I forgot to include that as a bullet on the slides. So just a reminder again, my name's Sean Phillips. There's my contact info, and if you have any questions, feel free to email me or call me at the number on the charts.
Great. Thank you, Sean. Any questions?
Thank you. It was very, very interesting to hear the detail. Gosh, I don't know what to do with this. But I was curious to know, you've talked about the SLS, V&V and the automation and testing. Is there a system of systems level test to integrate across the ground system, SLS, and
The SIL
Orion?
supports this. The SIL actually has emulators for the ground and for Orion, and so they do integration testing, cross-program integration testing. Not only there, but in each of the programs has their own labs where their software runs for real, and then we send emulators to them. I don't believe there's any system plan until the vehicle's put together where all three systems are actually running their own software in their native environments, though, at the same time.
Other questions? Nope. All right. Thank you.
Thank you.
Our next presenter.
Hi, my name is Scott Burley. I work at the Jet Propulsion Lab, and I will not be talking about flight software development and simulation. I will be talking about something entirely different. This will be reporting a little bit on some architectural work in delay-tolerant networking. For those of us here who don't know anything about delay-tolerant networking, none of this will make any sense at all. So, this would be a good time to get coffee or something. But if you know something about DTN, then I hope this will have some interest. The problem that we're looking at here in this particular context is scalability. DTN is well defined by now. It's tested. It's operational on space station. We're going to be baselining it for PACE, for Gateway, for other missions. It's a CCSDS standard, and it's well on its way to being standardized within the IETF as an internet standard as well. The problem there is success. As the scope of applications of DTN grows, the size of the networks is likely to grow. So how well is DTN going to scale up to these larger networks with more complex topologies? And there are sort of two general classes of obstacles to scalability for DTN. One is route computation in a delay-tolerant networking sort of takes two general paths. One is opportunistic routing, which is where you really don't have any idea what the topology of the network is. You just take your best guess and flood through the network and try to back off from flooding so you don't stress the network too much. And that's what all the many routing systems for opportunistic terrestrial delay-tolerant networking are based on, is essentially how do I not flood? How do I succeed without completely flooding the network? For spaceflight operations and for other environments in which we do know something about the topology, maybe and almost always a four-dimensional topology, that is, we know when there are going to be opportunities to transmit and when those opportunities will stop. For that sort of environment, we've been using for many years something called contact graph routing that charts paths through this four-dimensional contact topology, and that works well, but it is computation intensive. It's a lot of Dijkstra searches and so forth. It works fine, but for extremely large contact plans, the search time can be very long, and at some point it becomes untenable. So we need a mechanism by which the route calculation that you do at any single node is within some reasonable bounds, and that mechanism doesn't exist yet, and that's part of what I'll be talking about here. The other major sort of class of obstacles to scalability for delay-tolerant networking is that to enable DTN to work across a very broad range of operational scenarios and lots of different kinds of operational problems, you need a lot of knobs. You need a lot of things that you can tweak to adjust the way operations work for nodes in the network. And so the business of configuring a node in a delay-tolerant network so that it'll work properly with the rest of the network is pretty tedious. You need these kinds of information resources at every node. You need to know what are the protocols, the underlying protocols that you can use for point-to-point transmission, in the same way that in the internet you need to know whether you're using SONET or Ethernet or FDDI. You need to know the network topology, the four-dimensional network topology. When are the contacts going to arise? What are the limits on the transmission rates on those contacts? When are they going to stop? You need to know something about what the applications that they're going to be taking advantage of the capabilities of the node are going to need. What are the expectations that they're going to have of the service that the network is going to provide? And you really need, because this is really key, you need, for security in the network, you need to know encryption keys, security policy, potentially a lot of security configuration and tuning to make the operation of the network safe and reliable. So all that configuration currently is done using manual tools. There are mechanisms that we're developing in management protocols to make that work more efficiently than the prototypes that we've been using, but it's still heavily manual. The internet analogy would be that if you had to have a network manager configure every computer and every phone that used the internet, pretty soon it would not work anymore. And the way that the internet got around this problem is by using something called, well, one way anyway, is using something called DHCP. And so the intent here is to come up with something that is roughly analogous to the way DHCP works in the internet. Very roughly, but analogous in the sense that it fosters that sort of scalability. So you can think of this DTN node auto configuration that I'll be talking about here as being very roughly analogous to DHCP the idea being that if you have a DTN-capable device, a phone or a computer, that is equipped with this DNAC, then that when you start up a node, when you insert this device into the network, it can establish its own network identity. It can detect its own lower level communication resources. It can insert itself into the topology of the network, and it can form pathways for secure communication through the network automatically without somebody having to type a lot of things in. So we have some support for this concept in existing work. I'll talk about three sort of classes of supporting infrastructure that I think will help make this DNAC idea feasible. One is that we, years and years ago, and we've had it for a long time now, a standardized neighbor discovery protocol has existed, which enables a node to discover one or more existing topologically adjacent neighboring nodes. And it does that by listening for beacon tones on some general medium that everything in the network is supposed to have access to. Currently, there's a prototype protocol for this, IPND. There's a draft, internet draft for it that's been out for many years. It's been implemented in a number of DTN implementations, and it's based on the periodic broadcast of beacons over UDP broadcast. But you can easily imagine using an RF system or something along those lines as an alternative to that. The discovery of a neighbor enables the first little bit of knowledge of the topology of the network to be communicated to the new node. It also enables discovery of at least one underlying communication channel so that the node now can exchange the DTN bundles with at least one other node in the network once that neighbor discovery has happened. The second level of infrastructure here is public key infrastructure. Delay-tolerant public key infrastructure is a difficult problem for a number of reasons. The ordinary sort of PKI system that we use in the internet is not so good because it's based on client-server, which is innately non-delay tolerant. We do have a prototype implementation and design and internet draft of something called DTKA, a delay-tolerant key administration system that is based on publish subscribe rather than client-server. It establishes a trusted distributed key authority, and there's a multicasting of public keys that DTKA relies on that enables signatures and encryption to be implemented using the bundled protocol security blocks and defined for the bundled protocol throughout the network. And then the third element doesn't quite exist yet. There's been a lot of research in it. We don't yet have a solid prototype, but there have been experiments that are very promising, and that is a standardized hierarchical grouping system to locate each node inside a bounded region of network topology, roughly analogous to autonomous regions in the internet, very roughly. The regions are one-for-one with contact plans. That is to say, if a region is a set of nodes, then the contact plan that corresponds to that region is the set of all contacts that are planned between nodes within that region and no others. That means that if the size of a region is kept to a small number, if there are 30 odd or maybe up to 60 nodes in a region, the contact plan is going to be limited. It's going to be 100 or 200 contacts, which is something that you can reasonably search with Dijkstra searches in contact graph routing. What makes this scale up, we think, is that if these regions nest, if they are organized in a hierarchical fashion, then you don't really need a central database of which regions can talk to which other regions. Every region just knows that it can, every node knows that it can talk to everything else that's in its own region, and it can talk to a passageway node that is able to talk to things in the region that encompasses that region. And just by way of an illustration, and I won't try to go into this because it's a whole topic in itself, but you can, let's see, is there a pointer on here? Maybe. Is that where, yeah. You can imagine that if you've got a node in here and it needs to talk to a node over here, it can discover a way of talking to, well, it's not in my region here, so I'll ask my passageway to the outer region. The outer region says, oh, it's not in here. I'll ask this guy. This guy says, oh, it's not in here, but this guy might know. And eventually it percolates down, and the propagation of probe messages that discover the topology of the network automatically results in all of the passageway nodes learning which nodes they can convey bundles to and which ones they can't, so that subsequent communication from this node to this node follows a well-established path that doesn't have to be created manually. It just discovered automatically by the operation of the network. So, given all that infrastructure, here's what we're proposing we might be able to do by way of delay-tolerant network auto-configuration. And it's, I think there are 6 steps in what I've written up here. The first step is the new node needs to compute its own identity, which is in the spaceflight DTN world anyway, that would be a new node number. And there are a number of ways you can imagine doing that. One possibility might be that you can imagine that every node in the network maybe has an Ethernet interface to talk to other nodes on the spacecraft bus, or other nodes in the ground station. And in that case, maybe that Ethernet address can be embedded in some, you can have some function of that Ethernet address that becomes a unique identifying node within the entire network, and the node can discover that itself. Another possibility might be some combination of the current time and some sort of coordinates in a location in some common coordinate system. And there are a number of other things that we can explore for ways to select a node number that is known to be unique, and have each node discover that itself. Assuming that we can do that, the new node can compute its own private, public-private key pair. That's a straightforward thing. It's computationally intensive, but you only have to do it once, or very rarely. Maybe you roll over your keys every I don't know, year or something, but you shouldn't have to do it very often. The private key from this computation is stored locally at this new node. The public key is made available for publication. We can't publish it yet because we don't have anybody to talk to, but it's going to be directed to other entities so that they can encrypt things in that public key, which only this key can decrypt using its private key. The third step, the new node initiates operation of this neighbor discovery protocol. And so now it's listening for a neighbor, something else in the network, some other node that is topologically adjacent to it, so that it can communicate with directly. And until it finds that other neighbor, well, it's not going to be in the network. It's like it can't insert itself into the network until it finds at least one other neighboring node. And so it assumes that it's the only node in existence, that it's the only node in region 1, the universe node, And it's going to change its mind when it discovers another node, but that might happen right away, or it might not happen for some time. Eventually, the new node discovers its first neighbor, and that first neighbor in this context would be termed the new node's sponsor node, because that new neighboring node that is already part of the network is going to vouch for the new node to the rest of the network. The new node uses the newly identified common knowledge communication channel between itself and the neighbor to pass its own node number and its own public key, possibly some other credentials. We haven't worked all that out yet, to the sponsor node. And the sponsor node likewise passes its node number and its public key and some credentials perhaps back to the new node. The two nodes then, by some process we haven't yet worked out completely yet, verify each other's authenticity using some sort of credentials. Maybe that's something that's pre-placed on every vehicle, for example. But one way or another, the nodes determine that each one is authentic enough to proceed with the rest of the integration process. When that happens, the sponsor node tells the new node, here is your home region. Your home region is the same as my home region. You are now in my region. And the passageway node to the encompassing region for our region is this node XYZ. And here's the contact plan for this region that you have now entered. Now, there are no contacts with you yet. We need to work those out. We have discovered a contact, and that's fine, and we can schedule some contacts in the future. But for now, what I'm passing to you is, here's the contact plan for all the contacts among all nodes within your new home region. So if you need to talk to somebody in your home region, here's the plan you can use to figure the route for those bundles. The sponsor node then multicasts to all members of this home region a signed contact plan update message that inserts the new node into the contact plan. This is a registration contact which just basically says this node exists. It's a sort of a dummy contact. The start time is at the end of time, and the end time is like a second after that. But it's enough to insert it into the contact plan so that it's part of the region. And the sponsor node also multicasts to the network's distributed public key authority the signed assertion message asserting the public key of this new node. The public key authority then can include the new node's node number and public key in a message that it multicasts to everybody in the network who's interested in public keys, and in a bulletin. And there's a mechanism for doing that in a trustworthy fashion that we think is survivable against natural disasters and lots of different kinds of attacks. The new node then sends a probe bundle to node 0, the non-existent node. The probe bundle is passed to the passageway from the new node's home region to its outer region, to its encompassing region, and it's forwarded from there to all the other regions in the network. As that bundle is forwarded, it's not going to get anywhere because it's destined for a node that doesn't exist. But in the course of forwarding this probe bundle through the network, every passageway node in the network learns where in the network bundles coming from or going to this new node, what passageway to go through to exchange those bundles. And so the new node's location within the network is automatically communicated to all of the passageway nodes in the network, and thereby the new node becomes reachable from every node in the network. And this is all done automatically. So that's that's the summary slide for all of this discussion. Is we think that this general approach will enable delay-tolerant networks to scale up to quite large sizes, thousands, maybe millions of nodes, by leveraging hierarchical interregional routing and the automated self-configuration of new nodes that doesn't require hands-on management from network operators. And that's the end of my slides. Thank you very much.
Any questions?
So my question is, as soon as we get to the part of this process where there is a new node and a sponsor node, it is now asymmetric. So it makes sense if there's one node that is part of a larger network and one node that's just brand new off on its own. It's pretty obvious which should be which. But if you have two sort of established networks that wander into each other, how do we decide which one is going to play the part of the new node and which one is going to play the part of the sponsor?
That's a really good question, and we've explored that question to some degree, but we're still early enough in the process of working out the details of hierarchical interregional routing we don't really have an answer yet. We know the key principle here is that it's important for nodes strictly to nest. If there can be two nodes, for regions strictly to nest. So if there are two regions that come in contact with each other, they should come into contact in the sense that the passageways into those regions from the encompassing region come into contact with each other. And if that principle is preserved, then the architecture is sustained and the math of it all, I think, works properly. But it's a really good question. Something that came to me as I was talking about it was, oh, what if the first node it discovers is another new node, and neither one of them has anything? And that's another point that we're gonna have to figure out a way to make that work. I think these are questions that we can resolve within the context of this architecture, but they're not resolved yet.
So what happens if a node that's an intermediate node disappears for a while and then comes back? So that's going to be the case like if you have airplanes flying in the skies.
Can you speak up? I'm sorry.
So if you have like an airplane, it's going to be the case. Sometimes it's just not going to hear the signal.
Well, the loss of communication to a node that is a transient loss is something that delay-tolerant networking expects, right? That's built into the architecture. If it's an expected loss of connectivity, that should be reflected in the contact plan. If it's an unexpected loss of connectivity, that is a contact that you expect to have happen and it fails, then communication with that node is going to fail for whatever reason, and the reliability mechanisms for retransmission of lost data will start to kick in and say, oh, I'm trying to send to this guy, I can't send to him. At some point, that will raise a network anomaly, and then the question becomes, how do we deal with network anomalies? In the near term, network topology anomalies are going to be things that network managers are going to address manually. In the long term, something is going to need to be aware of those kinds of problems and make repairs to the contact plans for the network to account for that anomaly. We're not yet anywhere near being able to automate that, but it's clearly a capability that's going to be needed.
Anybody else? Okay, great. Thank you.
Thanks.
So we have a break till 3 o'clock.
A is a pre-existing node in the region. B is brand new that comes along and says, "Hi, I'm B," and A says, "Welcome to our region." At that point, B is part of the region. B has been inserted into the contact plan for that region.
So by virtue of the fact that C can't see B, he's part of it. So.
Yes, exactly. As soon as C comes along, C talks to B, doesn't know anything about A, but that's okay because B and A are both part of the region, they're both part of the same contact plan. There is indirect communication from C to A if there needs to be. Yeah.
So by that logic,
software, but we kind of have to provide requirements to flight software for what our functionality needs to be. And I kind of go through the process that we've been using for SLS the past 6 years, 7 years or so, and how we approach it. So over here is a lot of my co-authors, and there's some of the bigger leads across the SLS GNC. This work, though, goes across flight software, SLS, GNC, system engineering, M&FM, so there's a lot more people than just ones who are on here. And this effort's been going on for 8 years or so when we first did this study that led to how we're doing this now. So I have to make sure I account for a lot of people have contributed to this work over the years. So I kind of go through top-level GNC requirements, what our functional requirements look like, how we break it down into what our model-based approach is for our architecture, requirements, flight software, kind of go through our simulation side, how we provide that to flight software, and some of the processes back and forth we use to verify quality, functionality, that kind of stuff. So at a high level, from GNC, our high-level requirement is insert a payload into orbit with a given accuracy. So basically, we have orbital requirements, and we have to do this with a lot of caveats. So we have to do this safely, stably, be able to respond to abort conditions off nominal conditions and make sure the vehicle maintains stability, check for sensor health, quality, all that kind of stuff. But in the end, it's 3 metrics. How well are you in orbit to where you said you're going to go? So that's kind of our main metric that we have to always assess against in our simulations, and also that ties into when we do some of the SIL testing, incentive testing, we do hardware in the loop, how we compare back to what our results are, what our performance is from the GNC perspective. So from that, we have to go all the way from that vehicle spec down to our modeling simulation to the flight software and kind of full the whole loops to close our verification objectives. We kind of have to show that our sims work and also hardware works as well, and there's no unintended effects. So in terms of our GNC, just kind of quick overview what GNC is. Essentially, we take the input from the sensors, the RENU nav box, our rate sensors, the RGAs, and then our mission manager tells us what mode of flight we're in, what is our operational scenario, what kind of other health status kind of thing, and the abort conditions kind of thing. We feed it through our GNC block here. Basically, we have our nav, guidance, and controls, where basically we figure out where we're at, where we want to go, then how do we kind of get there. So all the way from reading in sensors out to our TVC, engine throttle, engine cutoff, those kind of commands to basically fly the vehicle. And we do a lot of Monte Carlo simulation with this, where we have this block here and implemented a big 6-off simulation, and we'll do Monte Carlo analysis to assess sensitivities, performance, all that kind of stuff to verify that the design for the sensors and our software here matches the requirements for the various scenarios. So in terms of how it's set up in terms of requirements-wise, so back in the days of Constellation, a lot of our work was all, the heritage method was all handwritten. We'd go off, do our analysis, design the algorithms, and then we'd write it down on paper and say, these are the requirements for the GNC flight software, hand them to the flight software guys, they would independently implement it, and then in the end we'd come back and we compare sims and make sure it all worked. That required a lot of paperwork, a lot of requirements, and we moved over from Constellation to SLS, intentionally driven decision to kind of reduce requirements on our side. So like I said, we reduce our requirements that are high level from the vehicle side to that one insertion requirement instead of having a bunch of high level requirements. We still decompose it internally, but traceability wise, we have those high level metrics that we track to it. And so we've kind of reduced this to make it a little easier for management. So kind of from that vehicle side here, we have level 1 where you kind of have the integrated whole vehicle stack, and level 2 for an integrated vehicle where you might have the core stage, the upper stage, the human caps, all that kind of stuff. This is kind of where we sit here, because we're GNC of the core stage with its engines, its sensors, its structure, all that kind of stuff. And then you go down a level deeper and you hit here where you hit the sensors, some of the hardware pieces, elements. For GNC side, we deal a lot with TVC, a lot with RENU, the RJ navigation sensors, make sure we understand what their software is, how they operate, and how that feeds into our performance analysis, and how we design our GNC algorithms. So that kind of goes into this design math model approach, where instead of capturing these things as requirements, we kind of capture them more so as models. And models in this sense might mean, for a nav sensor, it might be a software model of the RENU. Like this is a model of the RENU for performance that we validate against hardware. This may be a model of the FCOG selection algorithm. This may be a timing model. This may be a those kind of models take the place of requirements. So for our GNC system, our GNC will be a model of GNC instead of a bunch of shall statements that say implement this algorithm this way. And kind of because hey, here's a model, here's an implementation of it, and kind of go and place it that ways. We do a lot of physics-based modeling with the sim, so we have our 6-off sim here. We work with folks at Langley and other centers where we do shootouts a lot of the time to make sure that our simulations match theirs for our cross-verification results. And a lot of these parameters can go for requirements internally to us. So like some of our time-dependent parameters for data launch, so that kind of can be requirements to develop those variables for us. So in terms of how we're looking at GNC, so we have our little, basically our algorithm component block. And so this kind of started off, when we were first starting the program, as a way to say, instead of us writing down our requirements for GNC and describing it verbally, we wanted to be able to provide an executive model, because we do our analysis in a big 6-off sim in C. Our flight software guys write flight software in C. And so we are already kind of developing products that are very close to, but not flight software. We don't have a lot of the rigor in our testing, the rigor in the processes that our flight software group might have, but we do stuff that's dangerous enough to be flight software. So the idea was that take what we do and have this common model that captures our GNC algorithms that we can then use in our analysis tools in 6-off and feed it over to flight software. So in the end, when we go off to our software in the loop and the actual vehicle, that same piece of algorithmic code that we've generated with inputs from flight software and everything else is executed across the board. So we have good tie-in from how we've done our analysis to how it's implemented to how it's flying, to kind of get full insight to what's going on here. And there's less risk of having an algorithm change because of the way it was written down. It kind of gives us a lot of good insight to how it works on all these different platforms. So part of our DMM for our GNC includes executive algorithm, so it includes C code, parameter definitions, what our parameter files are for like all our inputs, a memo that describes the algorithms and the approaches, interface assumptions, what kind of data we're expecting where. So we have from our side, from the nav, we're very concerned about what the sensors put out, so making sure that the ICDs from the sensors match what's being fed in to the flight software, to the hardware managers, all that kind of stuff. So we kind of poke in little areas, make sure that things match what we expect them to do. And then our GNC model is pulled directly from our sim, allows us to tie back to our, every time we do a Monte Carlo simulation, we then tie it back to this code, have these results, so we can then do our own regression testing on our software to make sure it's still good, and also allows us, as we go into other comparisons, we can compare the Artemis framework with our solutions, with flight data eventually, and kind of compare across the board what we're doing. And so part of this process was to make sure we bring in the flight quality to us, because we don't do flight software code. We kind of developed this CR process where we go from our algorithm design to our 6-off analysis to eventually our model. We feed it over to flight software. They do a code review. We bring them in early to review our algorithms for their awareness, maybe say, hey, this is better from a flight software perspective. This fits better in the real-time environment than what you're doing here. And kind of fitting those things in, and through a CR process, those come back to us, and then we remodel on our side, redo our analysis, and mirror that the traceability as we change the code, as it changes the performance for what we're really concerned about. This whole process goes back through flight software implementation, software in the loop, and flight software qual. And there's always this feedback to our model where we can accept changes and make improvements, correct for any hardware issues that we see, and revalidate our performance results from a 6-off perspective. So in terms of this process flow, we do a lot of CR and repos on both sides of it. On this side, we kind of have our modeling on the GNC side, where we have our repositories here, our simulations. We have our comments here, our other documentation here. Early on, we did this. We also had to know that we can't just develop code that kind of willy-nilly. So we tried to bring in some coding assumptions, bring in what coding standards we could in terms of naming conventions, just the typical things you would see, and have reviews with that software, make sure we're doing things mostly in the right way. So that when we deliver it, it's for all of us, so it's kind of already taken care of. Similar to the way we do some like PPQ and RNA and kind of analysis, some static analysis before we deliver it, to make sure that we're kind of in the right direction, make sure we have a quality product going out. And then from that, the delivery of software, we sit inside of our GNC portion of here, and then from that testing area, you can get CRs back to us from that testing. Integrated flight testing give us CRs back, also testing our unit test cases. There's a lot of methods where, as assumptions we've made about how it runs on the hardware, we've had to iterate with that. There's a capability on these paths to go back to our design for them to be formally tracked for this. And as we do our various simulations, we can track our performance towards our high-level requirements as we go through all this. In terms of the actual process flow here, this kind of gets into more of the weeds, how we do this. So a lot of the standard software approach is still down here. A lot of the rigor in terms of your unit testing, the test cases, testing requirements is all still here. It's just kind of we plug in an element that's closer to what's needed in terms of the flight code implementation. So we go from our analysis process to develop an executable model that we can then deliver, taking in the coding standards, other inputs from flight software to drive how we implement the code. We develop algorithm test cases that say, as we develop this code, this is what it needs to do, this is the kind of performance we expect out of it, that goes along with it. So into our repo where we kind of track this stuff. And part of this too is we had to kind of formalize our processes a little bit more, especially as we get closer to flight code, flight algorithms, where we've hardened our CR process, our review process internally to make sure that everything is really traceable and has a lot of traceability and review before we release our models to flight software for implementation in flight. And then once we pass it over to the flight software group, then they do the flight code implementation, integration with the other drivers on the flight platform, the confidence test where they make sure that our implementation here matches on their side. So we provide unit test cases as well for over whole flight. The data is then fed on their side to make sure it matches what we ran in, to make sure the implementation is correct. We then do the full unit testing and then the software integration, and we do end up at this whole flight level test and hardware in the loop, where we then compare back the performance in their environment to performance in stick-off to make sure that we meet our performance we need under hardware latencies, hardware comm effects, all those other kind of things that you aren't really able to model in a software environment. So in terms of these verification, we implemented this throughout the system at multiple levels to track, make sure that our code is doing what it's expected to do. So at our GNC level, through our CR tool, we track the changes to it. We do a lot of iteration and regression test cases, looking at our performance metrics across guidance, dynamic control to make sure that we have understanding of our performance to our requirements. We do unit testing between Maverick releases, so as our base code changes, as our dynamics model changes, other flight inputs change, we have traceability so that we can say 5 versions ago, this is what the results were, they're still good, and as we make changes, we can see how the changes affect against our performance verification requirements. And then at the GNC model delivery, we then build a unit test case wrapped around that, basically from our simulation, take out the inputs from the sim, take the outputs of our GNC model, and then basically when we pull out the GNC model, we run that test again with those same inputs and verify we get the same outputs for that level of unit testing. And then we saw some issues because we're doing a lot of analysis on a x86 platform and not on a PowerPC. So when we switch platforms, we also have a flight-like processor that we do this on as well. So we'll take our flight code, move it over to the other platform, recompile it, rerun our unit test cases for validation down the line so that we can identify as we switch platforms, these things change due to rounding errors or just due to numerical precision kind of things between platforms. That gives us good traceability back from our analysis on our cluster to flight hardware, and then to its implementation on it, and so on and so on. Once that code is delivered to flight software, that same test is repeated, but now within a flight software architecture to make sure that we're still good on that side. And here, a lot of also our design level requirements, our software specifications kind of come into play, where we verify that the requirements for the code needs to do are written down, modeled, tested, validated for the flight quality and for the class day kind of software. And then at highest level here at the end, we get to the flight software system where we have integration modeling with all of the hardware DTUs, all the hardware simulators, where you can kind of come into play and say, now some of our models have changed, so instead of having software models of our sensors, we actually have development test units. So now we have the real flight software on those units in the loop, and our real FCOGs in the loop, our real timing in the loop, and now we kind of come through and see where any issues that we have in here. And we've kind of discovered some things through this, where some interface issues, we've identified things such as, right now our big focus is on latency. So we have software timing model, latency model, and stick-off, but we've been using our big simulation to actually go in and induce events so that we can model the latency of the system on the actual hardware with the actual software to validate some of our performance metrics and validate our performance. So in terms of our approach, we kind of have this common approach where we iteratively make our flight software. We iteratively work with flight software for their review, their inputs to it, updates to that for our modeling simulation, and how we port that over to flight software for that operation. And one of our keys is this, that instead of us having to, as another approach for smaller projects might take a different approach, where you might have a GNC flight code that's kind of a level away from when you actually did your analysis. But in this case, all of our performance results are the same algorithm, the same pseudocode as what's being applied. So it gives a lot of confidence in what we'll be able to do for that. And through this iterative process with flight software in the loop, we're able to maintain quality and do testing and make sure we have all the requirements that when it goes to be Class A software, it's ready for that, and it's able to easily become that through the processes and the rigor on our flight software group. Through a cross-discipline viewpoint, it eliminated a step for us having to basically write a document, feed over, someone else implement it, and then go back and verify it. So that paper document step is gone now because we have the model we hand off full of documentation and test cases. So that helps to remove risk in where error-prone process of making sure that your software designer who doesn't know GNC might misinterpret something, and we don't discover that until years down the road. Here we kind of have it already written out and defined, and in a way that's easily able to be understood by the software designer of all of our algorithms for kind of better understanding. We do test analysis across the entire board for this as we're doing it through. Part of the way to do this was bringing in the flat software architecture early, knowing what it did, how to integrate with them. So having our GNC and flat software teams kind of closely integrated and working together helped that a lot. So we have counterparts in the flat software and GNC side that we work very closely with in terms of all of our testing, reviewing results, developing code, and kind of make sure that they're all in the loop and understanding to what it's doing and how to approach it. And also enabled for this was having the tight CR on our side to manage our own code before we went out, so we understood what our changes were and traceability on our side. Some of our lessons learned from this is that it did reduce the requirements burden for what we need to do. That explicit thing was incredibly helpful to us, helped to understand any issues in implementation. As I mentioned before too, like we found, some of our big lesson learned here, I'll go at the bottom, was that in terms of our interfaces. So we found an issue where a misunderstanding of an interface caused basically an interface swap where we didn't expect it to be. And so that kind of gave insight to if you go kind of this approach where you're providing a flight software, it's also important to have requirements on the interfaces themselves, especially if you're real close to the hardware and say, we expect this message on this bus in this place in order for us to operate like we do, instead of having to check it in the back end of it. So having those requirements early on, defining hard requirements on inputs and outputs, is also incredibly helpful to manage those kind of risks. So part of our GNC model, like our new approach, kind of we had to kind of fit in with the way the sprints work, the way all the other processes work in flight software. But we have been able to work it out over the past couple of years. I think it's a pretty smooth process now, where we might be a little ahead of the next release of the flight software, but we kind of have worked out what that process looks like as we execute more and more. It's becoming a smoother process, in my opinion. And also for its components, as we go down to a lower level, as we're trying to model the software of other sensors, having good data there helped a lot to be able to provide that, having the data from the vendor in order to implement that. So for example, we have STDs, some of our small lower level components that we model and have traceability to and validation to, and that helps us drive validation through our whole entire simulation process for that. And also another key item we learned from this was that use the right model where you need it. So for example, if you're doing software testing, your model needs to include the interface to a high level of detail. Whereas if you're doing performance-based analysis, that might not be as important, but it's more important to match the error, the sticks, the behavior of it. And so knowing what model to put where makes the most sense. So for example, like a interface model might not go well in a 6-off Monte Carlo sim, where we don't care about like a bus interface thing. We can model that at a higher level, whereas you don't necessarily need high-level performance models that are exactly validated in your hardware loop platform because you're testing different things. So we've kind of seen those challenges, and we still have continually been improving both sides for better comparison between the two. So we can take our sim and their sim and basically do a cross shootout between our fully software 6-off and hardware loop 6-off on the other side. So there's been a lot of kind of lessons learned and things that we've done that have helped us kind of get a lot of insight into the flight software process, into what our code looks like, and eventually in order to be able to say that the GNC model as our design for our requirements works, and we have high confidence in that across the regime. So that's what I've got, and thank you very much, and I'll take any questions.
Questions?
Oh, Evan Anslone. Yeah, so I am one of the 12. Yeah, so I am right here, Evan Anslone. I am SOS Navigation. Naeem Ahmad is Guidance. Young Kim is one of our DLEs for vehicle management. Paul Wonderpoint is Flight Mechanics. Jimmy Compton is our secondary DLE for this. Stephen Huff is Controls. Thomas Parks Nav. John Wall is Controls. And Christian Garcia is our big software integrator for GNC systems.
So I have just a couple questions to clarify what you were saying. First of all, what do you mean by executable pseudocode? It seems like an oxymoron.
Well, it's actually, so I mean, we hand over C code, but because we aren't a flight software organization, we don't have the rigor. We're not CMI certified. We technically cannot make flight code. It's a model of flight code, so it's pseudocode. So it's not, it's kind of a verbiage. It's kind of how we get around the requirements and the procedures, right? So we make code that's of quality, that is a model of what the code will look like in flight, but once it's gone through the rigor and approval of the flight software process, it's not actually flight software yet. So that's kind of why I'm calling it pseudocode.
But it's actual C.
Yeah, it's actual C code.
Okay.
It is,
So-
it is C code with inputs. We have a data file that has all the binary inputs you read out, binary outputs you can compare it to. So our unit test case basically says you take our C code, you wrap it, you run it, it matches what we did on our side.
Okay, and the second thing that I have is kind of goes with that, and that is when your model is essentially the behavior of your algorithms that you expect it to do. And with the flight code, if they make tweaks to make things work, then how does that propagate backwards to you? How do you keep those things in sync?
Yeah, so that's that CR process that we've got on here. So those kind of algorithmic things, they can't really, part of the agreement was they can't change it. Basically, they put a CR and say, you need to change this for this reason. They put a CR in, and then we go in and change it. So if it's a wrapper thing of how you interface with it, that's kind of managed on their side. But if it's an internal algorithmic thing, so say, for example, we have a 1 Hertz guidance loop that won't run in our higher rate process, so we have to break it up. So we broke it up. That kind of thing came as a CR that said, hey, you need to re-implement this, do it this way. And then they formally gave us a CR, we accepted it, and we went implemented changes on our GNC model to account for that. So that's kind of how, if they see a tweak they want to make to it, it's supposed to go through this CR process back to us, and then we redeliver the next iteration of our model.
So they do their next iteration based on getting yours back forward?
Essentially.
Okay.
Yeah, so we'll deliver these models at regular intervals. So we have a verification level model, and then our last flight software drop was, I think, this spring. So our flight software is essentially done from the GNC perspective. So as they're doing testing and stuff, it goes through a very rigorous formal, like, we found this issue, this is what we want to change, and we kind of go through this whole loop over and over again.
Other questions?
If there was any change that you could make to the process, what would it be and why?
If anything, I would work more upfront on kind of making sure they understand, kind of sync up better with their sprint cycles on the site software development. Right now, we're kind of out of sync, and we kind of come, like, they'll come with a flight software release, say this date, and we'll come in 6 months early and develop our flight software. So I think tighter integration there and the processes could be useful, and better integrations between our teams and knowing when we release software to them and having that tighter role of be able to say, hey, we see this happening, can you change it quicker, and going on a quicker release schedule from our side. But that's limited because when we do a software release, we have to do Monte Carlo analysis and all this verification to make sure that we're still good. So that kind of limits how quickly we can move through this. And similar with flight software, like, it's not just us going in, it's all kinds of other stuff happening. And so it's kind of, we're kind of beholden to when that date can happen from their stuff, because they're integrating so much more than just our little piece of it. Because we're just one little piece of the whole software piece. So we can't hold them up from what we're doing. So to make sure we're done early ahead of that to integrate in.
Other questions? Great. Thank you, Evan.
Right, thank you.
Move that out of my way.
Yeah, that stand's becoming useless.
Huh?
The stand,
It may come
mic
in
stand's
useful, it
like
may-
useless.
sure, yeah, I don't know, we'll see. We'll see. All right. I want to be out here a little bit better. Okay. So I'm Brian Jameson, and I work in guidance, navigation, and control at Marshall Space Flight Center. My co-authors are Mike Hannon, Jim Cady, Juan Orphy, and Nick Olson. And this past year, we've been working in a project where we were doing a pilot evaluation of model-based design tooling for guidance, navigation, and control flight software. Let's see if I can. Is there somewhere that this has to point? Okay, I'm pointing it back there. Okay. And I'm pointing it back there. There it goes. Okay. Okay, so first of all, I haven't heard this term come up too much, I don't think. So maybe or maybe not, you know what model-based design is, but that's basically just you're using the model in the design process. And so what we're seeking to do here is we're seeking to systematically use models throughout the development process for requirements design, analysis, simulation, verification and validation, and documentation. Whereas a more document-driven system would be kind of the older method of doing it. And so we want to do that to automate our system and have a concurrent design process so that we can minimize human error, of course. And so probably many of you have seen this kind of a diagram where we have kind of the verification and validation V diagram over here on the right, where we want to iterate quickly and do small iterations each time we need to step through any of these parts of the verification and validation. So some of the improvements offered by model-based design include efficiency improvements by automating a lot of the aspects of requirements testing and documentation. And we've used a lot of MathWorks model-based design tools in our work for this evaluation. And one of the big advantages of that was that it includes model visualization that's naturally a part of the guidance, navigation, and control development process. And so since we're working with guidance, navigation, and control every day, and that's what Simulink is all about, that works well for us. So just a little bit of background pieces of information as was the previous one slide. This one, so if you, I don't know if any of you will recognize any of these slides that are shown, but Dr. Karen Gundy-Burlett presented here at this workshop about 3 different times in the past relative to the LADI mission experience and the model-based design that they were doing that was at a less developed stage of the MathWorks model-based design tooling, but they had good experience with that. She said that compared with using model-based design, hand coding the flight software would have taken longer and made collaboration more difficult. And so there was a lot of advantages that they found to this. I've got a picture. I'll let you read through the details later if you want. But basically, one of the advantages was that we weren't just throwing the model over the wall to the flight software folks. So I'm sure a lot of you would probably appreciate that. Hopefully we do a good enough job as we're going through this process to eliminate some of that. But here's an image, if it'll come up back there. Oops, wrong way. Okay. Here's an image of the spacecraft, right? Right? Okay, we're going the wrong direction. Sorry about that. And there it is. Okay, so it flew in 2013 and then was disposed of on the moon's surface in 2014. But they had a good experience with that. And so we were wanting to investigate a little bit more about that and implement some of that process for our procedures in the group that we were in. I will tell you a little bit more about that and that mission in a little bit. So, of course, MathWorks has done a lot with model-based design tooling. There's a poster here, but it's been produced by MathWorks. In fact, I can see the person who wrote the poster, but he worked with others, including some from Marshall and other places, I suppose, to produce that, and they've kind of synced that up really well with their design, with their tooling. So this process that they've developed covers a lot of 7150, including software requirements, design, implementation, and testing. It doesn't include things like architecture requirements and project management requirements, but pretty much everything you can, as I understand, with software requirements. And so one of the things that we've been doing as we've been implementing this model-based design approach is we've been meeting and consulting with the people here at Marshall Space Flight Center, the software people here, to make sure that we're not kind of getting out of sync and doing our own thing without, or that we're making sure that our process will work with theirs. Okay, I'm pointing it back there. And there we go, okay. Okay. All right. So, our project that we were on was called the Viper Lunar Lander. I'll tell you a little bit more about that in a bit. But we were using this project as a pilot project for doing model-based design of our guidance, navigation, control flight software development. So our goal was to apply this model-based design approach and tooling to condense our schedule, to reduce needed resources, and to improve the quality of the GNC flight software. So some of the expected benefits are that it would facilitate requirements, implementation, verification, and automate testing, several parts of testing, coding standard enforcement, code generation, static code analysis, and report generation. And in total, it would establish a highly automated, disciplined process that would allow repeated testing of the system throughout the design process. Now, I've got a picture there of the Viper lander. Just maybe a month or so ago, NASA put out a press release about the Viper rover, which so basically the plan is that with NASA going to the South Pole, I shouldn't say back to the South Pole, but going to the South Pole of the moon, they're planning on sending a rover there to map water ice and where that would be there at the South Pole of the moon. And so they released that, and this lander had been in development for delivering that rover. You can see it's kind of a pallet style. The solid rocket booster on the bottom would drop away some 8 or 10 kilometers above the surface, and you'd basically have a pallet that'd be landing on the lunar surface for the rover to drive off of. Unfortunately, at least in my view, but NASA decided they wanted to deliver that rover to the surface using the Commercial Lunar Payload Services contract. So basically using a company to do that. But then shortly after, or even more recently, I should say, here in the last few weeks, they released basically the design of this lander to the public so that they could bid for, we'd like to use these elements of it, or there's a white paper on it and things like that. So a lot of that's available now. I'm probably missing something that I wanted to tell you about that, but I guess you can answer questions if I did. Okay. All right, so kind of a core piece of our guidance, navigation, control development system is what we call affectionately GLASS. That I don't know that that's meant to imply that it breaks all the time. I think that's maybe more of an implication of it offering some better insight into our process. I don't know. I'm not the one who named it, but basically it stood for Generalized Lander Simulation and Simulink. It now handles more general spacecraft. It's 6 DOF, and so it's very well designed. Nick's the one who's kind of the lead on that, and it's very modern and flexible and user friendly. He's done a great job of updating it or ensuring that each time MATLAB releases a new version, that it's quickly checked out and make sure that it'll work for that one. So we're kind of up to date so far on being able to run in the most recent releases of MATLAB. So that's one of the nice things about it. And so it basically has this common core that has the dynamics in it, and then we can interchange the vehicle-specific plant models and the vehicle-specific guidance, navigation, control models into that core, or with that core, in GLASS. And of course, there's several advantages of this, including that we can do autocode, and that it interfaces with a lot of MathWorks tools. So there's a lot of capability there. So to take a high-level view of our process. So starting from the real world, of course, we want to use GLASS to model the real world and to produce our guidance, navigation, and control flight software. And so we have where we can check the requirements using Simulink requirements and Simulink test. We can, we're of course modeling with Simulink, and we can do code development there, and we can use Model Advisor in that process. We can also automatically generate reports, or do customized reports using the report generator. We can do Simulink, we can do unit testing using Simulink model and code coverage testing, and we can do autocode, of course, to be able to do the code testing using the embedded coder, and we can use the polyspace tools to do static code analysis, and all of that with the goal of producing quality autocode for our guidance, navigation, and control flight software. So looking at a little bit more at the kind of the first half here is what we've kind of gotten implemented so far in the process. It works out something like this. We started with our requirements in Excel in a spreadsheet up here, upper left. And so we can basically put our wording in there. That's kind of the blue column that you'll see there. And our specification values there in the kind of the orange column. And we can combine those using a simple formula. And so then we can have our requirement specifications that we're going to import directly into Simulink requirements to track. And so of course we can, well, I'll get back to that. We can also take the values that we've specified there into a Simulink data dictionary and use those in Simulink test and in the test harnesses and so forth, and tie those results directly in with Simulink test and its tracking of how we're doing it, following those requirements. We can also do unit testing and model coverage testing, and we can generate reports for that. And then of course all of that can be updated through a simple scripting and iteration to make sure that everything stays in sync there. Just to kind of walk through this, I produced a video to show you this, but there was some concern that I might not be able to email it to all the people that it had to get approved by, and so I now get to walk you through it. But basically, this process that I'll show you over the next 6 or 7 or 8 slides is basically a process that with 1 or 2 clicks of the mouse can update several things in the whole process. This is a rather simple example. We realize there'll be more complicated ones, but this one's kind of where we got with our initial start, and then there's a lot of stuff that kind of goes on underneath, or is potential underneath. And so with our spreadsheet, we've got our requirements here, and we're just going to go and we're going to test that. But then with these results, we can see here, in this case, we were just testing the 5 requirements there that you see in red or green. 2 of them passed and 3 of them failed. And so I wanted to, I guess I was just going to mention the irony that I'm clicking the mouse more time, or he is, than I would have to for this whole update process. Just to show you this because of the lack of the movie, just for the file size issue. But so with just 1 or 2 clicks, we can do this whole process. So we can see where we've got the failures. We can look at the cases we've got. In this case, we were doing Monte Carlo iterations of 200 apiece, and we were doing some landing precision tests. And so we can see where those failed. We can expand that out. That'd be the next slide. Am I in charge of that, or is he? I don't know yet. Okay, so we can just expand that out, and we can look at details of those iterations. Next, oh, there it is. Okay, and so we can dig into the details of those iterations and look at where we failed. In this particular case, our landing lateral speed was a little bit too high. And so for this simple example, we're just going to go to the next slide, and we're going to update some of the parameter values in our requirements. One of the things that I created in here was just a rather simple macro with Google's help to create highlighting and a note there in the spreadsheet to say, you've updated this, make sure that you're going through the process in the correct way to kind of get it through the system. Because it was a case, there'll be one or two of you here maybe who were, yeah, I'm seeing at least one familiar face who was there when I presented some of this before, and I did this and failed to go through the wrong way and broke the system, which helped me learn a thing or two. But basically, so now it's all automated, so that one, it's going to do this highlighting so that I'm careful about not about how I update it. I follow procedure as given on this red tab down at the bottom you see. But then with just a simple run of this script, just clicking on the button, clicking on just one click there, it'll basically, it's going to clean up my spreadsheet for me. It's going to import everything into the system. It's going to put those values now in the data dictionary for the simulation. And so this one thing I failed to mention earlier is basically this is doing it this way is allowing us to have a single source of input for all of our values for requirements testing. We're not having to put them into Simulink requirements and into the data dictionary separately. We're just importing them from here into both. And so just retesting that, we can see that we've passed, or essentially passed all of them that had the last 3 yet to go, but they did all pass, trust me. But basically that's the video, and so we can see that they all passed here in Simulink requirements. So that's a little bit of a quick run through of it. One of the other things that same script does is that it can produce reports. There's, of course, more generic reports available, but you can also customize some of your reporting. So that's what we were doing here with some. And then one of the other benefits of model-based design is the auto-coding, at least for us that is, since we're not super experts on some of that C++, like a lot of you guys are, I'm sure. But then it enforces some of those coding standards and make sure that we're consistent there. And of course, that's used by a number of folks. Now, just a quick detail, I guess a little bit more detail on that one. Basically, we've got our model here on the right, and the code that's produced for it is there more in the center, and along with the coding report, where you can dig into the details. You can see, you can't read it from where you are, I'm sure, but basically you can see that a lot of your commenting from your MATLAB scripting can go directly into the coding here to clarify what's going on and just make sure everything's clean for review. And then one of the nice things is that you can link between the model and the code, and so you can review some of those details a lot easier. Of course, we want to do coverage testing as well, and so there's linking there between the modeling and the code, and you can do that between, well, I should say, between the model and the test, and the code and the test, and so that eases repair of it and everything. Of course, we want to do static code. Okay, we want to do static code checking as well, and so we use the polyspace. The plan is to use the polyspace tools for that. We kind of just got started into that when MBD got in the way. OMB, whatever that's. All right, when the project was canceled, basically. That reminds me, one of the things I wanted to tell you was with this being, as we were developing this, we realized we wanted to work for plenty of other programs, and one of the plans at this point is to use it for possibly MAV, the Mars Ascent Vehicle that's been mentioned here. But that's kind of one of the things that with our developing this was to develop a process that would be useful across any program. So with that, of course, we want to check the static code analysis. The image at the right is of the Ariane 5 just moments before it began to break up, and then it's activated its self-destruct mechanism. You can kind of see that there's maybe I'm going to call it a 30-degree angle between the thrust vector and the rocket. About 2 seconds before this, they were pretty well lined up, but basically because of an arithmetic failure or overflow, the system failed. This is about 60-some seconds into the flight, and so it destroyed itself. So that's probably one of the most famous examples of you got to be careful with your code and doing static code checking. So just a few details here. I won't go into all of them, but basically, rather than doing the traditional document-centric development, we're wanting to do this model-based design approach to automate a lot of things in the process. Next. Okay, so basically we're wanting to fit a lot of pieces together of the puzzle to automate the process, to do testing, to do auto coding, and to do reporting, and I'll fit all these pieces together to have a highly automated system. In summary, we've developed a preliminary process to generate quality guidance, navigation, and control flight software code using model-based design tools as well as Excel. And we've also had our initial discussions, and we plan to have continuing discussions with the flight software people here at Marshall to make sure that we're working together. Our goals are to increase development speed, to reduce the amount of manual tasks we have to do, to improve the traceability from requirements to the model and code verification, and to ultimately produce high-quality GNC flight software. Are there any questions?
So you had talked about running Polyspace or other static analysis tools on the generated code to make sure it complies with coding standards, like MISRA, JSF, etc.
Yes.
Most of these standards were designed to catch the sort of errors that humans make when handwriting code. What sorts of errors have you typically seen in generated code, and do you think that perhaps different standards would be useful to check against?
Okay. Unfortunately, that was kind of one of the stages that we didn't really get very far to, nor was I the one who was working with Polyspace as much. Because of the cancellation of Viper, we're kind of stalled out on that. I know they had done some use of Polyspace. Jim Cady was the one who was working with that, and I think Nick as well. And I know they ran through the control portion of the code for some initial assurance on things there, but I don't know how much far. I don't think it got any farther than that. But if you want to contact them and ask them more details, you probably could.
Thanks for that presentation. Very interesting. Just one side remark. I think you wouldn't have caught the Ariane 5 problem with your approach, because the overflow was a result of a lot of other problems which you would not have discovered with autocoding and Polyspace.
Okay, I'm not an expert on that. I know MathWorks frequently, at least I believe they cite that as something that Polyspace would have caught. I apologize if I'm incorrect on that. I did read a little bit about that, and that was I guess you could probably talk with them for more details than I would know.
Other questions? Okay, great. Thank you. One technical problem to another. who's our next presenter? Looks like James Dabney. We'll get your slides up in just a second.
If I can figure this out. Okay. So I'm Jim Dabney, and my co-authors are Pavan Rajagopal of Geocontrols and Mike Facemeyer. Oops. Sorry. And Mike Facemeyer of the NASA IV&V facility. So this is what I'm going to talk about. It's an IV&V topic, so I'll give some background information and then talk about the BBN approach that we developed and some preliminary results. So as I said, that's the research team. And so we were talking a little bit earlier this afternoon about IV&V and what it is and what we do. So the main characteristics of it, first, it's independent from a managerial and technical and a financial perspective. And it's an analytical approach that we use. It's kind of a broad set of analytical tools that we use to evaluate the software for correctness and completeness. So it's not strictly a software discipline. It's rather a systems engineering discipline, but our focus at the NASA IV&V Center is on the software aspects of the system. So the scope for the IV&V Center is all of the NASA mission critical software. So that includes the HEO as well as science missions. The key information sources that goes into an IV&V project are the IV&V technical framework, which is the set of processes and tools that we use, as well as the developer artifacts, all of the artifacts that are produced in the development process. So there's, as we discussed earlier, because there's so many candidate projects for IV&V and such limited resources, it's necessary to determine first which projects are those that are the most deserving of IV&V. Certainly they all deserve it, but it has to be based upon some assessment of criticality and risk. And then once that's done, it's necessary to divide up IV&V resources among the projects, and then within a project to divide up the IV&V resources among all of the various analysis things that you could do. Because the set of things you could do even for one project is essentially infinite. You can never do too much verification. So the long-term project that we're working on is to use complete architecture information to identify and evaluate risk and to facilitate the IV&V planning process. Architecture information has certainly always been used by IV&V analysts to do the IV&V, but it's difficult to incorporate it into the early lifecycle planning process because there's not a lot of architecture information available. The information that's available is mostly development view kinds of things, and as a result, the planning processes has been more focused on that aspect, which leaves out a lot of the architecture information that is going to be accounted for in the development. So the goal of this process, this research line, is to incorporate the full architecture in the early life cycle process. And so the result of that is to identify the specific high-value assurance objectives and specifically things that aren't going to be visible just by subject matter expert review of requirements, and also to develop a reliable and repeatable process for doing that. So the previous work that we talked about here last year was we developed a mechanism to capture architecture, at least at a high-level perspective, really early in the project planning process, using all the available artifacts to capture all the architecture views, and we did that using a 4+1 model, as well as the cross-cutting concepts such as technical budgets. And based on that identification of the architecture, then we extended that to an approach to identify the set of risks associated with each of the architecture elements that we identified. And so that set of risks leads to the analysis work that IVNV is going to do. So this is the general overview of the scoping and planning process, particularly for the early life cycle. So the logical flow is first we determine what the architecture is, then we determine what the risks are associated with each of the architecture elements and cross-cutting concepts, and then from the risks we can identify assurance objectives, which are a set of questions or activities that the IVNV analysts are going to do to reduce uncertainty with respect to the risks. So we can category can call risks the things that can go wrong, which can be either operational or development. So development risks would be coding errors, testing errors, and operational risk would be the malfunctions of the system in operations, that things that aren't directly development related. In assurance objectives, as I said, they flow from the risks, and those are the set of things that the IVNV analysts are going to do to add assurance that the risks are controlled. So when we do those activities, we don't eliminate the risks, but we eliminate uncertainty with respect to the risks. So the risks are typically hierarchical, so a top-level risk might be the failure of some architectural element. So that could be a scenario that doesn't progress to completion correctly, or it could be a failure of another architectural element. And then supporting that are things that lead to that risk becoming manifested. And we want to decompose that down to the level where we can address the root causes of risks. And in some cases, a single supporting failure can cause an architectural element to fail. In others, it's going to take multiple failures together to cause that. So the risk the approach is that's used by the IVNV Center is the standard NASA risk cube, where we consider both the consequences of a risk and the likelihood that the risk will become manifest. The consequence is in terms of severity, and that's typically on a scale, usually 1 to 5. And likelihood is based on a similar kind of a scale, but the likelihood is determined from not from analysis of the consequences of it, but from the indicators of that risk. And so the indicators can be, we'll look at in a minute at a little bit more detail of them, but the indicators are things, characteristics of either the product or the process to develop the product that contribute to the risks or that reveal information about the risks. It's essential that the scoring that's done is accurate, both with respect to what the consequences are and the likelihood, because if they're not accurate, then it's going to result in dilution of the IVNV resources, putting resources where it's not going to give us the most benefit. And it's important that we identify the highest risk elements so that we can ensure that they get the proper attention. So this is a standard risk square that we have. You see it in both formats with either thing on the X and the Y coordinates, but the way that we're showing it here is with the consequence, which comes from analyzing what happens if the risk is manifest, and on the bottom, and then on the side is the likelihood, and the composite score, the product of those, is the overall risk score, and the red is bad and the green is good. So when we're doing the risk analysis, the consequence work is pretty much dependent on the system, and although it can be laborious, it's not going to be particularly controversial. The likelihood, on the other hand, is more difficult because we're trying to decide what's the relative probability using this 1 to 5 weighting of this particular bad thing happening compared to all the other bad things that can happen. And that's a little bit more challenging, in which led to this work. The traditional approach to doing the likelihood scoring is to use a set of basically adjectival kinds of characteristics in order to develop a numerical score. So we can divide them, the set that are here, the 6 that are here, the set that are currently being used. So from the environmental perspective is complexity, robustness, and testability, where complexity is how complex the function that's being implemented is, not necessarily the code. Robustness is the ability of the system or of that function to deal with uncertainty, and then testability is obvious. So those are the operational environment kinds of characteristics that deal with likelihood. And then the process characteristics have to do with the software development process, the amount of innovation in the process, the heritage and the information assurance are the characteristics that are currently being used. Those 6 characteristics have evolved over the years of the IV&V Center because they've been found to be pretty good indicators of whether something is likely to have a problem or not. The way that they have traditionally been combined is just computing a score based on a weighted sum of the scores on the 1 to 5 scale of each of the 6 characteristics. So it's just a linear combination of those 6 things gives you the likelihood score. The problem with that is at first it tends to push things towards the middle, and a second it's not typically standardized across the projects. So what we're working on with the Bayesian belief networks that we'll talk about next is a way of capturing the relationships among those in this case those 6 indicators, although it's certainly not necessary that we use that 6, in a way that accounts for the nonlinearities in the system, and the fact that sometimes some of them kind of cancel one another, and other times they reinforce one another. So in order to do that, the method that we developed uses a Bayesian belief network. So a Bayesian belief network is a probabilistic approach to combine evidence. So you can use a belief network in 2 main formats. You can use it to reason forward from a bunch of evidence to predict the likelihood of what's going to happen, or you can use it using Bayes' theorem reasoning backwards to take some event and determine determine the likelihood of each of the symptoms that contributed to that. So if you can use that, in other words, using it for diagnosis. So something bad happens. Why did it happen? That's the Bayes' theorem reasoning backwards. And the format that we're using it is, if one of these bad things happens, then what's the likely consequence of the system to fail? So it recognizes in this approach that the risks, the manifestations of the risk could be treated as a random variable with a probability density function that depends upon those risk indicators that we looked at on the previous slide. So this allows explicit modeling of the nonlinear behavior, and it gives us a way to exploit the expert opinion in a nice, clean format. So this is the basic structure of a node of a belief network. What the network represents is a causal relationship between 2 parameters that give us a random variable with a particular probability density function that depends on the values of those 2 parameters. And we can cascade those to form a network where the outer nodes are the inputs, and then the inner nodes are the causal relationships that work together. So this is the prototype network, a diagram of the prototype network that we developed for the likelihood estimation. So we have is that these two nodes are the two main categories, the environment and the process, and then the 6 indicators are the inputs to those. Now, the indicators can be a point value, or they can be a value with a tolerance. In the tolerance, and if you do that, then you can just use that as another random variable. And then, of course, those go together to create a random, the two inputs for the likelihood node, and then the output of that is a random variable that has a PDF that depends on that. So then we can evaluate the network using a Monte Carlo approach, and in order to do that, we need to have functions for each of the PDFs for each of these, in this case, those 3 nodes, environment, process, and then the likelihood. Oh, it went backwards. So the development of the node PDFs, each node, as I said, maps a set of inputs to a PDF, and it's not practical to calibrate for a system like this, to calibrate the network empirically, because it would require, in this case, thousands of software projects of the same kind in order to have a meaningful calibration. So instead, we do it using expert opinion. So essentially, what the network is doing is allowing us to capture knowledge from people that have a lot of experience. And the way that we capture the knowledge is using a simple PDF editor. And so what it's doing, if I look at the next slide, the PDFs are either a surface if there are 2 inputs, or a hypersurface if there are 3. And so what we're doing is developing control points for trapezoidal probability density function by locating key landmarks in that and boundary conditions, and then work back and forth between the editor, where we enter the PDFs by stretching the circles on the diagram. These little circles, you can grab those with a mouse and move them to sketch the PDFs. So what each of these is, this is the PDF that we expect if we have that 3 sets of inputs. And then we can again switch back and forth from the editor to the diagram until we get the PDF that makes sense. And then that whole network is evaluated using a Monte Carlo model. The IVNV Center uses MATLAB. We implemented it in MATLAB. And so for each Monte Carlo trial, you generate a random input, a random number using the PDFs that come out of the node to generate the inputs to the next succeeding node, and then do the same thing at the bottom level to get the likelihood score. And so we do that for a whole bunch of trials and get the statistics of the output. So we use the research team for the preliminary work to develop the node PDF tables, and we did it using the spreadsheet that is already being used for the planning. So it doesn't take any extra work for the planning thing. We'd use the exact same spreadsheet to do the inputs to the BBN, and it allows us to do that without doing any extra work. So this is an example of their spreadsheet for a hypothetical project with a set of capabilities. And so we have the scores, and in this case, it's set so that we have the estimate for the score, and we put it on a 1 to 10 scale instead of a 1 to 5, just because it gives us a little bit more discrimination. And then a tolerance above and below. And so there's going to be a separate Monte Carlo run for each of these capabilities. And this is the output of the nodes for one particular run. And so these are histograms that just shows you, using the Monte Carlo, what the PDF is for each of those nodes. And then that just shows you the expected value and the other statistics of each of the nodes. So the input data was easy to collect because they were using the same process that's been used in the past. We found that calibrating it was not that difficult a process of just iterating with those two diagrams, and it allows us to model the nonlinearities and to recognize the uncertainty in a nice, clean way. So in the future work is to continue to implement this on actual IVNV projects and refine the calibration based on project results. So that concludes the pitch. If there's any questions. I did okay.
Questions?
You were using a mean and variance, but is there any indicator that any of the data is actually normally distributed? Or is that just because it's a relatively limited range of things, it's close enough?
Well, we're not assuming anything is normally distributed. We're sketching the probability density functions using that trapezoidal PDF. So you can approximate a normal if that's what you think it looks like, but you don't have to. But any random variable has a mean and a variance, not just normal random variables. A uniform random variable has a mean and a variance. Those concepts aren't defined in terms of a Gaussian distribution. They're based on just the notion of distribution.
Well, there are PDFs that neither one of those actually exist, but there are more exotic PDFs where those numbers don't actually exist. So, but they're probably outside the scope of this.
So any other questions? All right, thanks.
Other questions? Okay, thank you.
All right, good afternoon. You can't tell me that you guys are all here to listen to a talk about cybersecurity, so it must be the free beer that's shortly after this talk. But either way, thanks for being here. Real quick before I get into this talk, how many people here are familiar with the concept of offensive security or red teaming? A couple? Okay, about half the room. So for those of you that aren't, it's where you use ethical hackers or adversaries to enumerate vulnerabilities in the system, as well as exercise the security apparatus of that organization. So, quick overview of what I'm going to talk about today. I'm going to give a background on my company and myself because I assume you're unfamiliar with a cybersecurity company from Maryland. We'll talk about cyber warfare in space, the state of cyber and space today, threats and vectors to space systems, and what tomorrow's going to look like. So not to grandstand, but again to give a frame of reference for the rest of this talk, 6Gen is a disabled veteran-owned small business out of Annapolis, Maryland that primarily does DoD certified red teaming, incident response, and high-tech, high-risk system vulnerability analysis. Locally, there's a few of us. We do space systems engineering, program integration, and cybersecurity. I'm local here in Huntsville. I have 14 years of experience in offensive security. I did it as a Marine and a contractor for the DoD, and I later did adversary emulation for Fortune 500 commercial clients as an ethical hacker. I've written a couple books on cybersecurity, red teaming, and cyber warfare, and I'm currently writing one about cybersecurity for space systems, so if you're interested in what I'm talking about today, feel free to help put my kids through college and buy a copy later this year. Currently, I do cybersecurity advising for a government customer on security strategy and integration. And one disclaimer before we get into anything else, I have never hacked a satellite, nor do I have any knowledge of a satellite being hacked. Everything I'm going to talk about today is purely based off the fact that I have a lot of offensive cybersecurity experience and some limited space system knowledge. Some of that was gained. 6Gen had a team. We went to DEF CON. If you're not familiar, it's the biggest international hacker conference held annually in Vegas. They have an IoT hacking competition, and we won that. And I'm sad to tell you all that the systems you all code for kind of bear a striking resemblance to a lot of IoT devices, right? Real-time operating systems, streamlined software, that sort of thing. And space systems are actually really juicy targets. You have IoT-like devices, you have SCADA devices to turn your antennas, you have traditional attack surface in your ground station with PCs and computers, and you communicate over the open air. So as an attacker, I appreciate a target like that. So let's talk about the boogeyman real quick. A little background on cyber warfare: it has a cost-benefit problem. So imagine you're going to fly a rescue mission into an enemy country, and you need a radar that is tied to anti-aircraft missiles disabled, right? If you tried to use cyber effects to disable that, it might take a while. You might not actually be able to access that system to disable it. When you execute your attack effect, you can't guarantee that it's going to work the way you wanted it to. I'm sure you are familiar with coding errors. And you can't do battle damage assessment. If I execute a cyber attack against an enemy radar, I don't necessarily have a good way of verifying that it has stopped working. Conversely, if I just blow it up with a missile, I can observe the missile striking the radar, I can see the crater afterwards, and if I'm flying the aircraft over that radar to go rescue people, I'm going to be a lot more comfortable seeing a crater in the earth as opposed to looking at what looks like an intact radar and going, gee, I hope those computer nerds did their job. So that's a problem everywhere but space. So in space, I actually don't want to do kinetic effects if I'm trying to disable something, right? If I hit a satellite with a missile and it's in a very popular orbital plane, I might be making a thousands of mile-an-hour shrapnel net that's going to interfere with potentially my own space vehicles or my allies. So being able to quietly disable or send a space vehicle to burn up in the atmosphere via a cyber attack is actually a much better way of going about that. So unfortunately for you all, the domain in which you code for is the most susceptible to cyber warfare because it's the most relevant. Additionally, any sort of cyber warfare that's going to happen in space, on a space vehicle, is going to be an attack against that vehicle and not for, say, intelligence gathering. If I wanted to see what you're doing with your satellite or alter an image that you took of my country to hide something, I'm just going to do that at your ground station, right? That's a normal computer that's familiar to me as an attacker. I don't need to bother trying to execute code in small communication windows on your space vehicle to prevent that sort of thing from happening. So the only reason I would go through the trouble of gaining remote code execution on a space vehicle would be to disable it or use it to launch attacks at other ground stations or other space vehicles. Tying all this together, I think we can all agree that almost exclusively the actors that are going to conduct cyber warfare or cyber actions against a space vehicle are going to be nation states. So you have the added benefit that the people going after your systems are well-resourced and willing to wait long periods of time to carry out their missions. So what is the state of cyber in space today? Systems on space vehicles are actually a kind of a precarious position. You have, resource-constrained, power-budgeted, streamlined software running on very limited systems, but the people attacking you have the benefit of modern technology and an internet full of exploits and that sort of thing. It's almost like targeting the internet of 20 years ago via the internet of today, right? So that is another thing that makes me happy as an attacker, that I look at the target set and I go, wow, it's more focused on functionality than security, right? Additionally, some talks earlier in this week talked about the move to Linux and away from real-time operating systems. As that continues to grow, obviously you as developers have the benefit that it's easier to write, drivers and code that are transportable to these systems because they're not custom one-off operating systems. But I'll tell you something, that hackers are developers too, and that means that any backdoors or exploits I write are also going to be more portable to those systems. And it means that as opposed to very unfamiliar computers that I try to attack, it now becomes something much more familiar, right? It looks like any Linux computer I might see connected to a terrestrial network. So Another thing that I heard talked about this week is an increase towards software-defined capabilities on space vehicles. I think that's great. That means that I have more things I can use to try to disable your satellite. So if you want to change, software-defined radios, I think, is the perfect example. You go from something that's pretty hardware-based to something that, if I can gain remote code execution on it, I can completely alter the way you communicate, right? So as those capabilities go more software-defined on space vehicles, there's more attack surface there for attackers to go after. There's also more code and attack surface to secure. So next, how many people in here are familiar with RMF? Nope, okay. So some of you in the government sector, it's a risk management framework put up by NIST. It's kind of a checklist and the closest thing to test and evaluation cybersecurity has in space. Unfortunately, it's currently not in a good spot. It roughly addresses the difference between a space vehicle and a terrestrial network by calling them out, but it's not really in a good spot to handle securing like a mesh of satellites, right? It doesn't cover what satellite-to-satellite communications might look like, or large sets of geographically diverse ground stations. So that's not that great of a spot, and that's the process the DoD uses to accredit its networks. There's also no widespread regulations for cybersecurity in space, which is kind of a problem. And unfortunately, in my opinion, cyber is not viewed as the highest risk to a space vehicle or its components. And as was mentioned earlier in the week by, I think, one of the MIT talks, right, just because it's not a cyber problem doesn't mean I can't use cyber to introduce it to your space vehicle. So if you use a software-defined capability to prevent something from happening like tumbling, I can then go after that and just make your space vehicle tumble. Or worst case scenario, I can at least prevent your capability from stopping the tumble. So I'm going to talk about threats to space vehicles. These are the ways as an attacker that I'm going to introduce something that's going to disable or damage the space vehicle. There's threats to the vehicle itself, and there's threats to the mission or the payload being run, as well as threats to other space systems and other ground stations. The examples I came up with were based on looking at small sats. That's obviously the most financially and operationally feasible space system currently out there. That's not to say that what I'm going to talk about won't happen on other space systems as well. Additionally, I think it's important to understand that ground stations will be compromised, right? That's not you're not safe because you're on a standalone ground station, and there's not a need for remote code execution vulnerabilities on space vehicle components for me to gain interactive access to those systems. If I can get access to the way you task your payload to do taking pictures, right, I could pass an infected tasking file up to the space vehicle that might get me remote code execution on your payload computer. Certainly, remote code execution vulnerabilities will enable me to do things like pivot around the space vehicle. If you're running things like OpenRTOS or VxWorks that have a lot of vulnerabilities in them, I can use that once I have access to the space vehicle via the payload computer to gain access to other things like the flight computer or the software-defined radio. One more thing before we get into the specific threats. I know that a lot of space vehicles are written with things like watchdog scripts and things like that, that if I tried to attack the satellite and disable something or try to draw down the battery, right, it might go into power saving mode and face the sun and hopefully wake back up. But you have to assume that if I'm executing arbitrary code on any of the competing devices on your space vehicle, I can certainly find those things and disable them. So threats to the vehicle, these are the threats that are specific to the space vehicle itself. Obviously, you have power being the biggest one. If there's no power on your space vehicle, it's not working. That's the most classic way I'm going to go after attacking it. And there's actually a bunch of different ways I can attack power, right? I can say affect the way you generate power. I can affect the efficiency with which you store power. I can affect power budgets. I could say, hey, whatever process, use all the power you want and drain the battery as often as you want, right? So it's not just one way to go against power. It's all the ways that are software-defined controls for generating, storing, and using power. Communication's another threat that's specific to the space vehicle. When we're talking about communication, it's if I can't talk to the satellite to fly it, or I can't task my payload, it might as well not be up there. So if I can affect your communications, you don't have a satellite. Lastly, I'm going to cover PNT for the vehicle. If the vehicle doesn't know where it is, what time it is, or what way it's facing, it can't do things like face your ground station to talk to you or turn towards the sun to recharge its batteries. And if it does have that knowledge but can't correct, right, you can't do things like avoid another space object or turn towards the sun to generate power, right? So you have to know that information, and then you have to be able to act on that information. Otherwise, your satellite's at risk of being non-operable. Obviously, any threat to the space vehicle itself is a threat to the mission it's conducting, but you could also, as an attacker, go after the mission specifically, because if I can talk to my satellite and it's flying around the Earth as I expect it to, but it's not taking pictures of what I want, again, it might as well not be there. So focusing in again on position navigation and timing knowledge, if my payload does things like take pictures, but it doesn't know what time it is or where it is or what way it's facing, you might get pictures of the stars or the open ocean when you don't care about it and things like that. And again, if you don't have the ability to correct, then you don't have the ability to adjust for the knowledge you do know about. There's two kinds of payloads mainly that I'll cover as far as threats to a mission. You have sensing payloads like an imaging satellite, and although I said editing a photo to hide something is something that an attacker would likely do on the ground, I could still attack the imaging portion of a satellite by, say, limiting its ability to focus or making a geofence in its configuration so that it just doesn't take pictures over certain areas. Emitting payloads are a little more interesting, where a sensing payload, I expect to get data down from the space vehicle, right? I expect to see the photos that I've tasked up to get taken. If the satellite does something like jamming and a hacker's used arbitrary code execution to turn off the jamming but make it report that it's still on, you don't really have a good way on the ground of verifying that that's still going on. So emitting payloads kind of have a situational awareness gap for stuff like that. But there's other emitting payloads like Sirius satellite radio, right? If I was trying to attack a payload like that, I'm just going to try to alter the way it broadcasts to the ground or the signal source itself. If your satellite's not receiving radio data, it can't transmit it back down to the customers. The last thing I'll cover as far as a threat to mission, but not the vehicle itself, are watchdogs and safeguards. By leaving them alone, but triggering them falsely, I could put your space vehicle in a continuous loop where it's reinstalling off what it thinks is a known good operating system over and over again because it thinks it has a problem. If that's happening, you're not really going to be able to task the satellite. Or I can do things like, say, convince the satellite that it's constantly low on power so that it constantly tries to face the sun and you can't take pictures of the things you want. This isn't an all-inclusive list, but these are just some of the general ones I wanted to cover. What do I mean by threats to others? So if you have multiple ground stations and something like an imaging satellite, and you infect payload tasking files and you gain execution on the payload computer, you could then infect what look like images to get downloaded by other ground stations and affect their computers as well. So in that way, we also need to think of the fact that space vehicles can be threats to other ground stations besides the one you've attacked it through, and they can also be threats to other space vehicles. As we approach large meshes of satellites, they're going to have ways in which they process and move data around the mesh to try to get it down to a ground station quicker, and you could potentially exploit the way that data moves around to compromise other space vehicles. The real takeaway here is that inherently space vehicle operations are trusted, right? The space vehicle trusts that what it's getting from the ground station is what it's supposed to get and vice versa, and as an attacker I can exploit that. Vectors are the ways in which I'm going to try to introduce these attack effects I've already discussed. You have the pre-operational phase, ground stations themselves, communications, bus to payload and vice versa, and kind of what I've already talked about a little bit is the vehicle to others. So pre-operational vectors are design, development, and the supply chain. If, as a hacker, I gain access to the computer you're doing your design on, well, now I know how to attack your satellite because I know how you're going to build it. If I gain access to the computers you're doing development on, I can append malicious code to programs before they're committed to your components. If I have access to your supply chain, well, I'm sorry, but it's probably over because you can do any number of things like install hardware backdoors that cut off power to the space vehicle after 50 hours of flight, right? And there's nothing you could really do to stop that. One other thing that's a little scary for space is the supply chain, the pool of vendors for space systems is very small. Somebody had a slide up showing, I think, 3 vendors for buses, right? There's probably not that many more that are popular and widely used. So as opposed to some other systems that could maybe order their servers and laptops from any number of vendors, space has a really small pool of the skilled technology vendors that provide parts. And that means that if a nation state is trying to do supply chain interdiction against your space system, they have a much smaller footprint that they have to worry about. So I'm only going to say a couple things about the ground station. Obviously, it's computers and servers, and that's traditionally what you understand to need cybersecurity and face cyber attacks. But I think what's important to take away is currently, due to the trust between space vehicles and the ground and vice versa, the ground station itself is the last layer of defense in depth, right? If there's nothing on the satellite to be suspicious of what it's getting from the ground station, we're in a bad spot, and that's something we need to address. Also, like I said earlier, if you have a ground station and you think because it's not connected to the internet, or it's a standalone server, or it's a closed network, that you're safe from cyber attack, I encourage you to do some research on the internet and find about how all of those systems have been compromised in the past. By communications vector, I mean the denial of communications or depletion of resources due to poorly implemented communications protocol. I think this is probably one of the areas where space is actually pretty mature. What we're talking about here is if instead of listening at set intervals, you listen all the time for a ground station, I can bombard your space vehicle with hellos and try to do communication handshakes, which can either clog up your networking and prevent legitimate ground stations from talking to you, or potentially deplete resources like power. The other thing about communication as an attack vector is that there's what seems to be a widely held belief that encryption means you're safe because I have a standalone server that I operate my satellite from, and it's an encrypted link over the air. I don't really have to worry about security, but encryption really needs to be looked at as a speed bump. Eventually it will be broken, and we should have some form of contingency or planning for the day that happens because space vehicles' lifespans are increasing in duration, and so is computing power, so there is a chance that the encryption you use to communicate to your satellite today could be broken tomorrow. When I talk about bus to payload vectors and vice versa, on the space vehicle, sometimes you might have your payload computer and your flight computer are physically separate devices, but maybe they have a shared resource that they both connect to, like GPS, for instance. If I can compromise your payload computer and I can mess with your GPS, I can affect your flight computer even though I have no other way of talking to it. And the opposite is true, of course. And then there's the logical separation. There's a lot of spacecraft design where one hard drive is maybe partitioned and used by several different functions on that space vehicle. The same with memory. If I gain arbitrary code execution, I can use the fact that I'm on the same hard drive as another part of your space vehicle to attack that from the portion I have compromised. Again, I kind of covered this earlier, but whether a compromised bus or a compromised payload on a space vehicle, I can use that to go after other vehicles in a mesh. I can use that to go after other ground stations and essentially make it a pivot point from which I can launch attacks. So what does tomorrow look like for cyber and space? Onboard computing resources are going to continue to evolve, right? We're going to get more and more computing power out of less power-hungry devices, and that means that traditional security practices should become more mainstream on things like space vehicles, but again, it also means that traditional attack vectors known to more and more adversaries will become more readily available. RMF and other processes that are used to have security checklists essentially for devices, they need to adapt because currently all they do is validate and verify that you've followed the procedures and closed ports and you're communicating the way you're supposed to. There's no real exercise of the security faculties on your space vehicle. It'd be like saying, well, I torqued all the bolts on the space vehicle to spec, so I don't need to do a vibe test, right? That's essentially what is the current operating standard for cybersecurity. Additionally, with the commercialization of space, right, we have space tourism up and coming, hopefully for some companies, they think, and that means that there's going to be loss of life consequences. I think it would be the end of both the people on board and the company operating the space vehicle if a cyber attacker did something like evacuate the pressure in the space vehicle. Right? So further, I think we need to have a continued education of both the space and security industries. I think that space is currently in a place, not for you all as developers necessarily, but in general where failure happens for a lot of different reasons because space is a tough environment to operate in. And by the time cyber becomes one of the larger problems for space, it's going to be too late to address that problem. And I also, speaking as a cybersecurity professional, not a lot of us know enough about the constraints that you all code to as far as power budgets and resources to really provide security solutions that are going to work in conjunction with your code on the space vehicles that we're talking about. And so I think education on both sides is necessary. And again, by the time cyber is among the highest risks for systems in space, I think both industries need to be prepared to implement solutions for that. That's it.
Ready for questions? Questions?
So I saw you give us a bunch of kind of, this is how bad it could be. Have you seen any successful interventions so far, or are there other industries we can look at that have similarly harsh environments?
Have I seen any successful what, sorry?
Interventions.
Like stopping an attack? Or preparing for one? I think the closest analogy the space industry has is really the IoT industry and maybe even SCADA. Those have certainly blown up in cybersecurity recently over the past 5 years, and there's been a lot of attention to how do we do like lightweight security services to things like, you know, the computers that control fire alarms and sprinklers, or, you know, even in your guys' case, rotate antennas. So I would try to take lessons learned from that and how they've implemented lightweight security in those realms and try to apply it to space, if that makes sense.
So do you know, I mean, the gut reaction is that military classified missions aren't going to share their defenses because they're afraid of people discovering their vulnerabilities. But you look at the open source and the open protocols of the internet and how that has gained robustness by having red teams all the time.
Yep.
Do you think there's any interest in the military in saying, let's put these out there for people to attack and find our vulnerabilities instead of keeping it secret?
Yep, so that's a good question. I do know that at DEF CON next year in 2020, the National Security Agency, I believe, is the government organization. They plan to have a satellite that you can communicate with that they want people to go and attack. I don't know if they plan on sharing the results of that or what exactly the motivation is. But I think from the offensive cyber perspective, right, the fact that that sort of thing is happening at DEF CON means that security is starting to realize that space is blowing up and that maybe it's kind of a blind spot for us. So I hope that that increases over time.
So the analogy between space and embedded is certainly true in terms of the types of processors and constraints. The biggest difference that springs to mind offhand is that in space often there is development assurance and standards that the systems are being developed to. It's not necessarily something where it's a strict cost constraint on making the cheapest possible software. I'm wondering if the development assurance process might be a good springboard for addressing some of these attacks, or if there's ways of tweaking it to take security into mind, or if you think that's a red herring and it's fundamentally a different thing.
No, I think that especially some of the standards you guys have levied on you know, doing flight stuff with NASA and things like that, those are definitely a step in the right direction, and I agree there are things that in the IoT realm you really don't see. I'd like to think that the regulatory hoops you guys have to jump through would make sure that you don't have hard-coded credentials stored right on board the device and things like that. So I do think that there's a bit of a leg up, but I would also caution, like I said, It's not necessary that remote code execution vulnerabilities are going to be necessary to impact a space vehicle from a compromised ground station. If I can learn enough about the way you task it from the ground, right, I can abuse that to do things, because assumingly you're running with some sort of mediumly privileged context to do the things you're doing on the space vehicle, if I can pass up what look like legitimate instructions that I think are going to affect it, I can still attack it that way.
Yes. So even in the non-space arena, hello? Oh. Even in the non-space arena, there's often a spirit of non-sharing with the idea of proprietary software and hardware. And this does apply in this situation as well. What do you think that companies, not just the government, could do to try to promote a more open kind of collaboration in the spirit of security enhancements?
I think space is probably already kind of along the path to solving that issue, because you're moving towards more standardized implementations of things. As you adopt stuff like Linux operating systems, instead of writing one-off pieces of real-time operating software, you're creating a bigger community to contribute to those things. I do understand that there is that proprietary issue, and that companies might try to not disclose, just as the government might not, as was mentioned by the gentleman over here. But I think space is on the way to getting there.
So you mentioned earlier that Linux is actually potentially a big attack vector because the hackers know it quite well. Would you say that it would be safer to run like a BSD distribution instead of a Linux distribution, or would that not necessarily make things safer? No.
No, I mean, I apologize for using Linux to describe any sort of normal operating system, but the takeaway there is that as you as developers use things that are more like normal computers, your systems are going to be, to me, it's going to look like just another computer out there, right? If I'm riding SpaceWire, but I still get to talk TCP/IP, and it still has Linuxy things or Unixy things on it, then I know how to interact with that device.
Great, thank you. So the last thing for today is we have a city official, happens to be my wife, city council member. She wanted to do a welcome from the city for everybody, and I think she has five reasons to stay in Huntsville.
I thought that was going to snow last night.
That was not a reason to stay in Huntsville, because if you're expecting that all the time,
Microphone up there.
that rarely happens. So, Ken, but yes, that was big, very, very big news. So I am Frances Akridge, and Mr. Scott Akridge found me when I was minding my own business in Washington, D.C. one night at a jazz concert, and I heard someone say, "Hi, you." So I'm going to project my teacher voice and not use this.
Nobody online can hear you, so they didn't come to Huntsville, so.
If you're not in Huntsville, you're in the wrong place, and I'm going to give you 5 reasons why. Here we go. And I have my poor man's BlackBerry. I'm of that generation. I still think of it as a BlackBerry instead of my iPod, right? So, excuse me, iPad. Diversity, your daily life. Daily life here, hopefully you have a taste of what it's like to live in Huntsville. Whether it's dining out, going to play, you probably didn't have time yet for going for a walk on any of our 5,000 acres of land, the land trust and the trails. But it is finally, after 10 years, when I got here 13 years ago, Huntsville was just a place, it was a nice place to raise your family. That was a big honor for me. Even though I was happily married, we are very active, and I wanted to have something more to do than just go to the kids' softball games. In the last 10 years, it has exploded with things to do, from craft beer to video arcades to axe throwing to top golf. If it's in a big city, we have it now in Huntsville without the big city hassles. Our cost of living is 25% less in housing than any other city in the United States. So when I came here from Washington, D.C., I had the same salary, and I took a 25% raise especially in housing, was much less. So that is a huge advantage. Food costs are also a little bit less. Clothing, it's the same, but we buy it online most of the time if you buy clothes. Recreation, I like to call it recreation. Whether you want to find just the right church, we have all of them. Sometimes more than one on a corner, it's kind of cannibalizing each other, but also through recreating our spirits and our souls through the arts, whether that's culture, whether that's performing arts, or the visual arts. It is a blooming business and environment here. In fact, we just hired the very first music audit in the United States, had a consultant come, and unlike some consultants who look at your watch and tell you what time it was, they actually helped us define what our music culture, what we can do to expand it. Because we have a lot of people like you who are really good in math, we have a lot of people who are really good in music. A luthier who's in Low Mill makes $3,000 guitars, and he was the upper stage manager for the Aries program. So we have people with lots of different skills and lots of creativity here. That creativity is also found in just an entrepreneurial spirit, whether it's from Wikipedia or comments sold, or who's the guy that's on Friday, Getting Smarter Every Day? Anybody watch his YouTube video?
Yes.
I forget his name, but he's here, and he has that's a big business for him, Getting Smarter Every Day. Our diversity, not only in housing choices. If you come back to Huntsville to visit and think about living here, you'll find every lifestyle, any kind of apartment you want. You can have an apartment right next to the Bridge Street Shopping Center. It can be out in the valley. You can have land anywhere in the region. Get yourself a farmette. It was in the New York Times about a guy that bought a $250,000 about 7-acre farmette. Would have cost him $500,000 in New York. So we have a wide variety of lifestyles and housing, and I'm really proud to say a big variety of people who live here. 10% of the people who live in the Huntsville metropolitan area that were born in another country. So about 100 different languages are spoken here. We have about 50% of us come from someplace else. So it's a wide mix of people, and we're really proud of that. And lastly, the jobs. Not only is it in advanced manufacturing, and Dr. Oakley, please come back, by the way, for the jobs. There you are. We're building a magnet cyber high school here, and so we'd love to have you come back as an adjunct professor or head of the thing, okay? But, well, that would be somebody else's job right now. But anyway, but Deloitte did a survey for the Chamber of Commerce and one of the mayor's initiatives. They interviewed 96 companies. In the next 3 years, they all anticipate adding a total of 14,000 jobs. With a multiplier of 2.5, so we're up to about, what, 25,000 jobs. But the 14,000 are in your purview for the next 3 years. So come back in lots of sectors: biotech, cyber, defense, agriculture, all of them supported by 5 different colleges and universities, some of them famous for their research. I'm very proud of the Hudson Alpha Institute for Biotechnology. Not only are they a research nonprofit organization, but they also have now 32 spin-off companies. They only started with 8 when the 2 partners put that together. But it is a model. They do genomic studies for agriculture, and they do genome work for medicine as well. And all of those things add up to just a really great lifestyle here. So please come back. The mayor, our city council, all of the Huntsville welcomes you to come back and consider living in this great city. And in the end, our motto is, we are building an inclusive community. All are welcome here. My cards are here on this table. If you have any questions about what it's like to be here in Huntsville, I can give you a good idea, because not only am I the city council person for the east side of the city, but I myself was a transplant, so I can help you navigate that Thank you for your attention.
All right, we won't take any questions. So we have the Straight Dale Distillery tour. We're going to leave right outside the door here in about 5 minutes. I'll be walking over there with you guys. The mugs and modeling, of course, starts in the art room like now. When we walk out of the room, you can go up there. The dinner's 6:30 tonight.